What if everything you've ever known, every star in the night sky, every moment of your life, even the universe itself, wasn't the original, but just a reflection? A cosmic echo rippling through an unimaginable sea of realities. It sounds like science fiction, but right now, some of the brightest minds in physics are running simulations that suggest this might not just be possible, it could be the truth. 48 separate experiments, each more intricate than the last, are pointing to a staggering idea. Our universe might be one of many, a single note in a symphony of parallel existences. And if that's true, it would rewrite everything we thought we understood about reality. Think about the last time you stood in a canyon and shouted, only to hear your voice bounce back at you moments later. Now picture that same principle applied to the fabric of existence. What if the Big Bang wasn't a one-time event, but a reverberation, a cosmic echo from another universe's collapse? Or what if the strange behavior of particles at the quantum level isn't random chaos, but the faint whispers of other realities brushing against our own? These simulations aren't just wild guesses. They're built on the cutting edge of physics, weaving together clues from cosmic inflation, dark matter, and even the mysterious patterns left behind by the birth of the universe. The results are so compelling that scientists are starting to ask, are we living in the original or just a copy? This isn't just about abstract theories. If these simulations are right, it would mean that somewhere out there, versions of you might be living different lives in different universes, each shaped by tiny variations in the laws of physics. It would mean that black holes could be portals, that time might not flow in one direction, and that the very nature of reality is far stranger than we ever dared to dream. So buckle up, because we're about to dive deep into those 48 simulations, unraveling the science behind them and exploring the jaw-dropping implications. By the end of this journey, you might never look at the night sky or yourself the same way again. The question isn't just, are we alone? It's, are we the only version of us? And the answer might be waiting in the echoes. The multiverse isn't just one idea, it's a tapestry of theories, each weaving its own version of reality. Picture a vast ocean where every bubble rising to the surface is a self-contained universe, floating alongside countless others. That's the bubble multiverse concept, born from cosmic inflation, the idea that our universe expanded faster than light in its earliest moments. If inflation can happen once, why not over and over, birthing new universes with every burst? But then there's the quantum side of things. Imagine every choice you've ever made, what to eat, which path to take, splitting reality into alternate versions where each possibility plays out. This is the many worlds interpretation, where every quantum decision branches into a new timeline, creating infinite variations of you, living infinite lives. And let's not forget string theory, which suggests our universe might be one slice of a higher dimensional brain, vibrating alongside others like sheets in a cosmic stack. These aren't just wild imaginings, they're frameworks backed by equations, tested against the edges of our understanding. The common thread, our universe might not be special. It might just be one page in a library so vast, we can't even comprehend its size. That's what makes these 48 simulations so electrifying. They're not just playing with ideas, they're stress testing them, hunting for cracks in reality that could reveal the fingerprints of other worlds. Take the cosmic microwave background, the afterglow of the Big Bang. Some simulations suggest its faint, unexplained patterns could be Bruises, places where our universe bumped into another. Or consider dark matter, the invisible glue holding galaxies together. Could it be particles leaking in from a neighboring universe? even black holes, those cosmic vacuum cleaners, might be doors to elsewhere, their singularities birthing new universes in their collapse. These simulations are detectives, piecing together clues that could rewrite the story of everything. And if they're right, the multiverse isn't science fiction. It's science fact waiting to be proven. To understand how these 48 simulations could shake the foundations of cosmology, you have to grasp just how far virtual experiments have pushed our understanding of the cosmos. Think of it like this: if the universe is a puzzle with missing pieces, simulations are the hands that let scientists test how those pieces might fit without waiting billions of years to see the results. Supercomputers don't just crunch numbers, they build entire universes from scratch, governed by the laws of physics we know, and sometimes by the ones we're still guessing at. Every galaxy, every particle collision, every ripple in space-time can be modeled down to mind-bending precision. But here's where it gets wild. These aren't just reruns of our own universe's history. Scientists tweak the variables altering the strength of gravity, the mass of neutrinos, even the number of dimensions, to ask one electrifying question: what if things were different? That's the power behind these 48 experiments. Some focus on cosmic inflation, replaying the Big Bang with slight twists to see if other universes could sprout like bubbles in a boiling pot. Others dive into quantum mechanics, simulating how particles might entangle across realities, or how black holes could stitch space-time into bridges between worlds. There are even models exploring phantom energy, a hypothetical force so extreme it could tear the fabric of reality, leaving behind scars that might connect us to other dimensions. What unites them all is a single, thrilling possibility: that our universe's quirks, the way galaxies cluster, the mysterious smoothness of the cosmic microwave background, aren't accidents. They could be signatures of something grander, like waves from a distant shore finally reaching us. But simulations aren't crystal balls, they're mirrors reflecting both our genius and our blind spots. For every breakthrough, there's a challenge. How do you simulate something as bizarre as a multiverse when we're not even sure what rules it follows? That's why these 48 projects are so meticulous. They cross-check each other, hunting for patterns that hold up no matter how you tweak the math. When multiple simulations point to the same anomaly, like strange voids in the cosmos where gravity behaves oddly, it's not just a glitch. It could be a clue, a cosmic breadcrumb leading us toward the unimaginable. The most exciting part: we're not just passive observers in this detective story. With every simulation, we're peering deeper into the shadows, asking the universe to reveal its best-kept secret, whether we're alone in the dark or just one voice in a chorus of realities. Imagine the universe in its first moments, not as a single point of light, but as a runaway explosion of space itself, stretching faster than light could chase it. This is cosmic inflation, the theory that our universe ballooned from smaller than an atom to cosmic size in less than a blink. But what if that expansion wasn't flawless? What if it left behind wrinkles not just in space, but in time? That's exactly what the first of these groundbreaking simulations set out to explore. By tweaking the parameters of inflation, adjusting its speed, its energy, even the way it ended, scientists recreated those first moments in staggering detail. And what they found wasn't just randomness. Hidden in the cosmic microwave background, that ancient afterglow of the Big Bang, were faint, ring-like patterns. Not imperfections, but fingerprints. The simulation suggested these could be bruises from collisions with other universes, like bubbles bumping together in a froth of reality. Picture it: another universe with its own laws of physics, brushing against ours in those chaotic early moments, leaving behind a mark we're only now learning to read. Here's what makes this so revolutionary. The cosmic microwave background has always been our universe's baby picture, a snapshot from when everything was just cooling off. But if these patterns are real, they're not just baby photos, they're family portraits, showing distant cosmic relatives we never knew existed. The simulation didn't just predict these echoes, it matched them to real, unexplained anomalies in the data we've collected. Areas where the temperature fluctuates just a little too much, or the polarization of light bends in ways that don't quite fit our models. These could be the scars of a multiverse, subtle but undeniable. And the implications, they're staggering. If inflation can create bubbles and those bubbles can collide, then our universe isn't just one of many, it's part of a network. A cosmic neighborhood where the walls between worlds are thinner than we ever imagined. Maybe dark energy, that mysterious force accelerating the universe's expansion, isn't some fundamental property of space. Maybe it's the lingering push from a long-ago collision with another reality. Or perhaps those odd voids in space where galaxies seem to avoid clustering aren't empty by chance. They're the shadows of where another universe once touched ours. This simulation isn't just a thought experiment. It's a roadmap pointing telescopes and satellites toward specific patches of sky, hunting for those telltale rings with ever sharper precision. If we find them, it won't just confirm the multiverse, it'll tell us something profound about our place in it. We might not be the original universe, we might not even be unique. But we could be the first to reach out and touch the reflections in the cosmic mirror. Quantum mechanics has always been a realm of the bizarre where particles appear and vanish in the blink of an eye, where reality seems to flicker like a candle in the wind. But what if these quantum fluctuations aren't just random noise? What if they're part of a hidden pattern, a cosmic design so vast it repeats itself across every scale of existence? That's the startling possibility unearthed by the second of these groundbreaking simulations. Picture a snowflake, its intricate branches repeating in smaller and smaller versions of themselves, creating a structure that's infinitely detailed no matter how close you look. Now imagine that same principle applied to the fabric of spacetime itself. This simulation didn't just model quantum fluctuations, it treated them like fractals, mathematical shapes that echo their own patterns endlessly. The results were staggering. The chaotic dance of particles popping in and out of existence wasn't chaos at all. It was a symphony of self-repeating geometry, with the same structures appearing in the quantum foam as in the clustering of galaxies billions of light years apart. Here's why that's revolutionary. If the universe's smallest scales mirror its largest, it suggests something profound, a hidden order woven into reality, like a signature from something or someone far beyond our understanding. Think of it as finding the same fingerprint on a grain of sand and a mountain. It defies coincidence, it hints at design, and if that design holds, it could mean our universe isn't just one note in the cosmic chorus, it's part of an infinite fractal, branching into other realities where the same patterns play out in endless variations. The simulation took this idea even further. By mapping quantum fluctuations against the large-scale structure of the cosmos, the way galaxies form vast, web-like filaments across the void, it found eerie similarities. The voids between galaxies matched the gaps in quantum foam. The clusters of matter echoed the clustering of particles at the smallest scales. It's as if the universe is a hall of mirrors, reflecting its own blueprint at every level. And if that's true, it raises a spine-tingling question. Could these fractal patterns be the stitches holding the multiverse together? But here's where it gets even stranger. Fractals aren't just pretty math, they're the language of growth, of systems building upon themselves. If the universe follows fractal rules, it might not have been born just once. It could be constantly unfolding, birthing new versions of itself in an endless cascade. Every quantum fluctuation, every particle's brief flicker into existence, might be a tiny universe sprouting into being, only to vanish moments later. Our reality could be one stable branch in an infinite tree of possibilities, with other branches thriving or collapsing in dimensions we can't even perceive. This simulation doesn't just challenge our understanding of the cosmos, it redefines what reality might even be. If the quantum and the cosmic are fractal reflections of each other, then the multiverse isn't just out there. It's in here, woven into the very fabric of our existence. And that means every time you look up at the night sky, you might not just be seeing stars. You might be staring into a mirror, gazing at a pattern that repeats forever. Black holes have always been cosmic enigmas, places where gravity is so strong, not even light can escape. But what if these monstrous voids aren't just dead ends? What if they're gateways, tunnels stitching the fabric of reality together? That's the radical possibility at the heart of the third simulation, which didn't just study black holes, it treated them as potential bridges to other universes. At the center of this experiment was a simple but profound question. If information falls into a black hole, where does it actually go? The simulation mapped the journey of particles crossing the event horizon, that point of no return, but with a twist. Instead of vanishing forever, the data suggested something astonishing. The particles didn't just disappear, their properties began to mirror patterns found in quantum entanglement, where particles remain mysteriously linked across vast distances. It's as if the black hole wasn't destroying information, it was translating it, imprinting it onto the fabric of space-time itself. And here's where it gets even stranger. The simulation revealed unexpected symmetries in the way black holes radiate energy, a phenomenon known as Hawking radiation. Normally, this radiation seems random, like static from a broken radio. But when researchers tweaked the model to account for potential connections to other universes, the static began to form patterns, faint, repeating sequences that resembled echoes. Not echoes of sound, but of structure, as if the black hole was acting like a cosmic tuning fork, vibrating in harmony with realities beyond our own. This isn't just theoretical sleight of hand. If black holes truly are gateways, their behavior could explain some of the universe's most baffling mysteries. Take dark matter, for example. What if it's not an invisible particle at all, but the gravitational shadow of matter from a neighboring universe leaking through these cosmic tunnels? Or consider the bizarre way some black holes spin far faster than our models predict. Could that excess energy come from being tethered to another reality, like a door slightly ajar, letting in a draft from another world? The implications are dizzying. If black holes link universes, then every one we've observed, from the supermassive beasts at the centers of galaxies to the tiny, primordial ones left over from the Big Bang, could be a potential passageway. A cosmic subway system connecting infinite versions of reality. And if that's true, then the information we thought was lost inside black holes, it might not be gone. It might just be somewhere else, echoing across the multiverse, waiting to be decoded. This simulation doesn't just challenge our understanding of black holes, it reimagines them. Not as tombs, but as translators. Not as endings, but as beginnings. And if future observations match these predictions, we might be staring at the first hard evidence that we're not alone in the cosmos. We're just one room in an endless mansion of universes, all connected by the darkest doors imaginable. Dark energy has long been the universe's most perplexing riddle, an invisible force pushing galaxies apart faster and faster, as if space itself has a hidden accelerator pedal. But what if this mysterious energy isn't constant? What if it's just one setting on a cosmic dial with other universes tuned to entirely different frequencies? That's the jaw-dropping revelation from the fourth simulation, which didn't just study dark energy, it played with it, twisting its strength across countless multiverse scenarios to see what would happen. The results were like stepping into a hall of funhouse mirrors, each reflecting a distorted version of reality. In some simulations, dark energy was weaker, just a nudge, barely enough to counteract gravity. Those universes collapsed inward early, stars and galaxies snuffed out in a crushing embrace before life could even spark. Others cranked dark energy up to extremes, expanding so violently that matter was ripped apart before it could form planets, let alone people. But nestled between these extremes was a razor-thin sweet spot, a Goldilocks zone where dark energy's push was strong enough to keep the cosmos open, but gentle enough to let galaxies, stars, and ultimately us emerge. Here's the spine-tingling part. Our universe doesn't just happen to land in that perfect balance. The simulation revealed something far stranger. The value of dark energy we observe isn't just likely, it's statistically inevitable if life exists to measure it. Think of it like tuning a radio. Most settings are static, but a few let music through. We don't hear the static because we're here in the one channel where the signal is clear. This isn't coincidence, it's a clue that our universe might be one of countless others, each with its own dark energy setting, most barren, a few just right for life. But the simulation dug deeper. By mapping how dark energy's strength affects the cosmic web, the vast filamentary structure binding galaxies together, it found eerie echoes of fine-tuning. Slightly more dark energy and galaxies would be too scattered for stars to ignite, slightly less, and the universe would be a dense, overcrowded tangle. Our reality walks a tightrope between these extremes, suggesting something profound. If dark energy is variable across the multiverse, then our existence isn't just lucky. It's a fingerprint of a deeper principle, a law that favors universes where life can arise to witness them. This isn't just about cosmology. If dark energy's value isn't fixed but floats across realities, it implies something staggering about the nature of existence. The force we thought was fundamental might be local, a quirk of our cosmic neighborhood. Other universes could be out there, their skies stretching faster or slower, their fates written in equations we've barely glimpsed. And if that's true, then the mystery of dark energy isn't just a puzzle to solve. It's a message, a breadcrumb leading us toward the multiverse's grandest truth. That reality isn't a single story. It's a library with our universe just one volume on an infinite shelf. We often think of the Big Bang as the ultimate beginning, a moment when time, space, and everything we know burst into existence from nothingness. But what if that explosive birth wasn't the start of the story at all? What if it was just the latest chapter in an endless cycle of cosmic rebirth? That's the mind-bending possibility explored in the fifth simulation, which dared to ask, could the Big Bang have been a rebound, a universe bouncing back from collapse like a phoenix rising from its own ashes? This model didn't just tweak the parameters of our universe's infancy. It rewrote the script entirely, treating the Big Bang not as a singularity, but as the turning point in an eternal loop. Picture a stretched rubber band snapping back, except instead of rubber, it's space-time itself. The simulation traced the hypothetical collapse of a previous universe, crunching down under its own gravity until it reached a point of unimaginable density, and then, instead of vanishing into nothingness, it rebounded. The energy of that collapse didn't disappear, it transformed, fueling the explosive expansion we call the Big Bang. But here's where it gets truly astonishing. The simulation didn't just theorize, it hunted for fingerprints. If our universe was born from a bounce, the violent energies of that transition would have left ripples in spacetime itself, faint gravitational waves echoing through the cosmos like cosmic aftershocks. These wouldn't be the ordinary gravitational waves we've detected from colliding black holes. They'd be primordial, woven into the fabric of existence from the first moments, carrying whispers of the universe that came before ours. And the most electrifying part, we might have already glimpsed them. In 2015, researchers studying the cosmic microwave background reported a curious signal, a faint twisting pattern in the polarization of ancient light. At the time, it was dismissed as noise, but this simulation suggests it could be something far more profound, the imprint of pre-Big Bang physics, a relic of the universe's last gasp before it rebounded into our reality. The implications are staggering. If the Big Bang was a bounce, then time itself might be circular, not linear. The universe wouldn't have a true beginning or end, just endless cycles of expansion and contraction, each one rewriting the laws of physics in its wake. Stars, galaxies, even life might arise again and again in slightly different forms, like variations on a cosmic theme. And if that's true, then the mysteries we've been chasing, dark energy's acceleration, the universe's perplexing flatness, could all be clues left behind by the universe that came before us, like a message in a bottle washed ashore from another time. This simulation doesn't just challenge our understanding of origins, it redefines them. The Big Bang might not be a beginning, but a turning point. And if future gravitational wave detectors catch those primordial echoes, we might finally have proof that our universe isn't the first, and it won't be the last. The cosmic microwave background is more than just an ancient glow. It's a time capsule, a snapshot of the universe when it was just 380,000 years old. But what if hidden in that faint radiation are not just clues about our past, but messages from other realities? That's the bold question driving the sixth simulation, which scoured the CMB for anomalies so strange they defy conventional explanation and might just be the fingerprints of parallel universes brushing up against our own. Imagine looking at a photograph and spotting a shadow that doesn't belong, a faint, unexplained blur at the edge of the frame. The CMB has its own version of this, a massive cold spot, a region chillingly devoid of the expected radiation, stretching across billions of light years. At first, scientists dismissed it as a statistical fluke, but this simulation treated it like a detective examining a crime scene, reconstructing every possible scenario to explain its origin. The most startling conclusion, that cold spot could be a cosmic bruise, a place where our universe once collided with another, draining energy from the impact like a scar in spacetime. But the anomalies don't stop there. The CMB isn't perfectly uniform as you'd expect from a smooth Big Bang. Instead, it's lopsided, with one hemisphere slightly warmer than the other, a cosmic asymmetry that defies standard physics. When the simulation tweaked its parameters to account for a multiverse, something remarkable happened. Those asymmetries began to align with predictions of neighboring universes exerting gravitational tugs on ours in those first moments, like invisible hands pressing against the fabric of reality. Here's why this is revolutionary. If the CMB's quirks are truly imprints from other universes, they're not just curiosities, they're roadmaps. The cold spot size and temperature profile, for instance, match what you'd expect if another bubble universe grazed ours during inflation, leaving behind a void in its wake. The asymmetry, it could be evidence of a larger multiverse structure, with our universe tilted like a ship caught in the wake of a passing giant, and the implications are staggering. If these anomalies hold up under deeper scrutiny, they'd be the first tangible evidence that we're not alone in the cosmic ocean, just one island in an archipelago of realities. Future telescopes, like the European Space Agency's Euclid mission, could hunt for more of these fingerprints, turning the CMB from a relic into a portal. Every unexplained fluctuation, every odd pattern, might be a message in a bottle, washed ashore from a universe we've yet to imagine. This simulation doesn't just challenge our understanding of the CMB, it transforms it from a baby picture into a family album, one where the faces in the background aren't strangers, but reflections of realities we're only beginning to glimpse. And if we learn to read those reflections, we might discover that the universe has been whispering its secrets to us all along, hidden in the static of the sky. String theory has long been the wild frontier of physics, a realm where tiny, vibrating strings replace particles, and the fabric of reality dances to the tune of 11 dimensions. But what if those vibrations aren't just the music of our universe? What if they're harmonies in a cosmic choir resonating across countless others? That's the breathtaking vision behind the seventh simulation, which didn't just explore string theory, it mapped its hidden landscapes, revealing how universes with entirely different laws of physics might brush against ours, leaving behind echoes we're only now learning to hear. Picture a grand piano with an infinite number of keys, each one playing a different set of physical constants, some where gravity is stronger, others where light moves slower. This is the landscape of string theory, a vast, multidimensional terrain where every valley and peak represents a possible universe with its own unique rules. The simulation didn't just chart this abstract terrain, it brought it to life, modeling how these universes could collide, merge, or even shatter like cosmic symbols. And the results were electrifying. When two such universes interacted, their vibrations didn't cancel out. They created standing waves, resonant frequencies that lingered long after the collision, like the hum of a tuning fork struck in another dimension. Here's where it gets eerie. These resonant frequencies wouldn't just vanish into the void. They'd imprint onto the fabric of space-time itself, potentially manifesting in our universe as subtle anomalies, places where gravity flickers unexpectedly, or particles behave as if tugged by invisible strings. Think of it like hearing a distant orchestra through a wall. You might not see the musicians, but the vibrations reach you all the same. The simulation identified specific patterns to hunt for, strange symmetries in the distribution of galaxies, or energy fluctuations in empty space that defy conventional physics. These wouldn't be random noise, they'd be signatures of other realities, vibrating just out of phase with our own. But the real breakthrough came when the simulation linked these resonances to one of the universe's most puzzling features, dark flow. That's the mysterious phenomenon where entire galaxy clusters seem to drift in the same direction, as if pulled by something beyond the observable cosmos. Conventional physics chalks it up to statistical error, but what if it's not an error at all? The simulation showed that a neighboring universe, vibrating at a resonant frequency with ours, could exert just enough gravitational pull to create this cosmic current. It wouldn't be a collision in the traditional sense, more like two sheets of paper sliding past each other in a breeze, close enough to feel the ripple but never touching. This isn't just theoretical poetry. If these string theory landscapes are real, they'd rewrite our understanding of reality's building blocks. The fundamental constants we take for granted, the speed of light, the strength of gravity, might not be fundamental at all. They could be local, like the climate of a single valley in an endless mountain range. Other universes might have entirely different weather, with laws so alien we can barely simulate them. Yet through these resonant echoes, we might catch glimpses of those distant realms, like hearing a song played in a foreign key, the simulation's most tantalizing suggestion. That we're not just passive observers in this symphony. If resonant frequencies connect universes, we might one day learn to tune in, not with telescopes, but with detectors sensitive to the subtle tremors of space-time itself. Future experiments could hunt for these vibrations in the hum of gravitational waves, or in the way particles twitch when no one's looking. And if we find them, it won't just prove the multiverse. It'll mean we've been sharing the stage all along, performing in a concert where every note is a universe and every silence, the space between the stars, might just be the pause before another verse begins. Time feels like the most familiar force in our lives, always flowing forward, never backward, carrying us from past to future like a river with one current. But what if that's just an illusion, a quirk of our particular universe? Simulation 8 dared to ask a question that flips our intuition on its head. What if time's arrow isn't fixed? What if, in other universes, it points in the opposite direction, or doesn't point at all? The key to this mystery lies in entropy, the universe's tendency toward disorder. Here, entropy always increases, which is why eggs don't unscramble and coffee never unstirs itself. But this simulation didn't just accept that rule as universal. It tweaked the fundamental laws, creating virtual universes where entropy behaved differently, sometimes decreasing, sometimes fluctuating randomly. The results were mind-bending. In certain configurations, time didn't march forward. It flowed backward, with cause and effect reversing like a film played in rewind. Particles would uncollide, shattered glass would leap back into whole panes, and memories might form of events that hadn't happened yet. But here's where it gets even stranger. These backward time universes didn't exist in isolation. The simulation revealed that under specific conditions, they could entangle with forward time universes like ours, creating bridges where quantum particles could communicate across the divide. Imagine two clocks ticking in opposite directions, yet somehow still synchronized. This isn't just theoretical sleight of hand. Real-world quantum experiments have already shown particles influencing each other instantaneously across vast distances, a phenomenon Einstein called spooky action at a distance. But this simulation suggests something even wilder. That spookiness might not be limited to space. It could stretch across time itself, with particles in our universe entangled with their past or future selves in another. The implications are dizzying. If time's arrow isn't fixed, then the one-way flow we experience might not be a law of nature, just a local byproduct of how our universe cooled after the Big Bang. Other realities could have entirely different relationships with time, some where the future influences the past, others where time loops like a Möbius strip. And if entanglement truly crosses these boundaries, it could explain some of quantum mechanics' most baffling quirks, like why particles seem to know each other's states faster than light can travel between them. They might not be communicating across space, but across time streams, with echoes from alternate realities whispering through the quantum foam. This simulation doesn't just challenge our understanding of time, it shatters it. The past, present, and future might not be the rigid structure we thought. They could be fluid, interchangeable, even simultaneous in the grand tapestry of the multiverse. And if that's true, then every moment we experience, every choice, every memory might be rippling outward, touching versions of ourselves in realities where time runs backward, sideways, or not at all. The arrow of time isn't just pointing forward. It might be pointing everywhere at once. Neutrinos are the ultimate cosmic ghosts, particles so elusive they can pass through light years of lead without a single interaction. Billions stream through your body every second, leaving no trace. Yet these phantoms might be hiding the universe's best-kept secret, cracks in reality itself. The ninth simulation didn't just study neutrinos, it turned them into detectives, hunting for whispers from dimensions beyond our own. The mystery starts with something called the neutrino anomaly. These particles shouldn't have mass according to the standard model of physics, yet they do, wobbling between different flavors as they travel in ways that defy easy explanation. The simulation tackled this puzzle head-on, modeling how neutrinos might behave if they weren't just passing through our universe, but brushing against others. The results were startling. Certain oscillation patterns, those strange flavor shifts, matched predictions for particles that occasionally leak into extra dimensions or parallel branes, like echoes bouncing between unseen walls. Imagine throwing a pebble into a pond, only to watch the ripples vanish mid-spread, not because they've faded, but because they've slipped into another pond entirely. That's what neutrinos might be doing. The simulation revealed specific energy signatures where particles seem to lose momentum not to collisions, but to brief dips into other realms, dragging back traces of those journeys in their wobbles. Even more compelling, these anomalies aren't random. They cluster at energies that align perfectly with theoretical models of compactified dimensions, tiny, curled-up spaces predicted by string theory, too small to see but large enough for neutrinos to dance through. Here's where it gets eerie. Deep underground, in labs like IceCube and Super Kamiokande, scientists have recorded neutrino events that shouldn't exist, particles arriving with energies so high they'd need cosmic accelerators we've never observed. The simulation offered a radical explanation. What if these aren't from our universe at all? What if they're strays flung into our dimension by violent events in a neighboring reality? Picture a supernova exploding in another brane, its shockwaves punching through the fabric between worlds, sending neutrinos screaming into our detectors like bullets from another time. This isn't just about solving a physics puzzle. If neutrinos are cosmic border hoppers, they could be our first functional tool for probing the multiverse. Future experiments could look for telltale gaps in neutrino flux-specific energies where particles vanish en masse, suggesting not detection failures but departures. Or they might hunt for mirror neutrinos, particles that arrive with spins reversed, as if reflecting off a surface we can't see. Each anomaly would be a breadcrumb, leading us deeper into the labyrinth of realities. The simulation's boldest suggestion, that we've been misreading neutrinos all along. Their weirdness isn't a bug in the universe's code, it's a feature, a signpost pointing beyond the edges of our reality. And if that's true, then every neutrino passing through you right now might be more than a ghost. It could be a messenger carrying secrets from worlds where the rules are different and the possibilities endless. What if everything you see, every star, every galaxy, even your own hands, isn't truly three-dimensional, but an incredibly convincing illusion? Like a cosmic mirage projected from the edges of reality itself. That's the radical idea at the heart of Simulation 10, which didn't just model the universe, it treated the entire cosmos as a hologram, a shimmering reflection of information encoded on a distant, two-dimensional surface. The holographic principle sounds like science fiction, but it's rooted in some of the most profound puzzles of physics. Black holes, for instance, pose a bizarre conundrum. When matter falls in, what happens to the information it carries? Quantum mechanics says information can't be destroyed, but general relativity suggests it's lost forever in the singularity. The simulation tackled this paradox by imagining our universe not as a volume, but as a boundary, a vast spherical shell where every event inside is actually encoded on its surface, like a movie projected from the walls of a theater onto the space within. Here's where things get mesmerizing. The simulation recreated the quantum entanglement of particles, those spooky connections Einstein hated but with a twist. Instead of linking points in three-dimensional space, the entangled pairs were mirrored by correlations on the hypothetical 2D boundary, and the patterns matched perfectly, as if the 3D universe was just a shadow play cast by data flickering on the edge of existence. Even more startling, the math suggested that the information needed to describe everything inside a region of space, every atom, every photon, could fit on its surface with no loss, like compressing a library into the text on its door. This isn't just abstract theorizing. The simulation hunted for real-world echoes of this holographic effect in the cosmic microwave background. Tiny, hexagon-shaped patterns in the CMB's polarization, long dismissed as noise, turned out to align eerily with how information might pixelate if projected from a lower dimensional surface. Think of it like seeing the graininess of a photograph blown up too large. Those hexagonal flickers could be the universe's pixels, hints that we're living inside a cosmic projection. But the implications go far beyond pretty math. If the holographic principle is true, it means the solid, tangible world we experience is a kind of optical trick, a 3D rendering of data stored on some unimaginably distant horizon. Gravity might not be a fundamental force, but a side effect of that encoding process, like the way a video game's physics engine emerges from lines of code. Even time itself could be part of the illusion, a narrative woven by the hologram to make sense of the underlying data, the most mind-bending takeaway. This simulation suggests that black holes aren't just objects in space, they might be the universe's way of testing its own limits. When matter crosses a black hole's event horizon, it's not truly destroyed. It's transcribed onto the boundary like ink pressed onto a page. In a holographic cosmos, nothing is ever lost, just translated into another form, waiting to be read by whoever or whatever knows the language of reality's source code. So the next time you look up at the night sky, consider this. The stars might not be distant suns, but brushstrokes on a canvas we can't see, painted by a hand we've yet to understand. And if that's true, then the greatest mystery isn't what lies beyond our universe, it's what lies beneath it, in the hidden dimension where reality is written in light. Gravity feels like the most constant force in our lives. What goes up must come down, a rule as dependable as sunrise. But what if that reliability is just a cosmic coincidence, a lucky roll of the dice in a multiverse where most realities aren't so stable? Simulation 11 took gravity's so-called universal constant and tossed it into the cosmic spin cycle, tweaking its strength across countless virtual universes to see what would happen. The results were chilling. Our universe's gravity isn't just right for life, it's improbably, vanishingly precise, like finding a single grain of sand perfectly balanced on a mountain peak. Start with a universe where gravity is just a fraction stronger. Stars burn hotter and faster, their fuel exhausted in millions of years instead of billions, far too quickly for planets to form, let alone life. Galaxies collapse into dense knots, their stars crammed so close that solar systems are torn apart by tidal forces before they can mature. Now flip the dial the other way, gravity weaker, its pull a gentle whisper. Matter drifts like fog, never clumping enough to ignite stars. The cosmos becomes a dark, featureless expanse, forever stuck in childhood. But here's the twist the simulation revealed. Between these extremes lies a razor-thin sliver where gravity is just strong enough to bind galaxies but gentle enough to let them breathe, a balance so delicate it defies randomness. To get a universe like ours, gravity's strength must be fine-tuned to roughly 1 part in 10 to the 60th power. That's like throwing a dart across the observable universe and hitting a bullseye the size of a single atom. The implications are staggering. If gravity's value isn't fixed by some fundamental law but floats across the multiverse, then our existence isn't just lucky, it's statistically miraculous. Like a cosmic version of Goldilocks, we find ourselves in the one reality where the porridge isn't too hot or too cold, but there's a darker edge to this discovery. Most simulated universes weren't just hostile to life, they were hostile to structure itself, collapsing into black holes or evaporating into voids before even reaching maturity. Our universe isn't just rare, it might be one of the only possible configurations where complexity, let alone consciousness, could ever emerge, yet the simulation didn't stop there. By mapping how gravity's strength affects the cosmic web, the vast filamentary scaffolding of galaxies, it found something eerie. In universes where gravity was even slightly off, the web unraveled. Too strong, and it became a dense, knotted tangle. Too weak, and it frayed into disconnected wisps. Only in a narrow range did the web form the elegant, sponge-like structure we see in our own cosmos, a structure that, not coincidentally, provides the perfect highways for matter to flow into galaxies and stars to ignite. This isn't just about gravity, it's a clue that the laws we take for granted might not be laws at all, just local bylaws in a multiverse where every possible variation plays out. And if that's true, then the force that keeps our feet on the ground might be more than a constant. It could be a signature, a fingerprint left by the universes that didn't make the cut, countless echoes that collapsed or dissipated before they could ever be heard. We're not just living in a finely tuned universe, we're living in the echo of a much larger, much stranger reality. Quantum entanglement has long been physics' most baffling magic trick. Particles born together remain mysteriously linked, instantaneously mirroring each other's states no matter how far apart they drift. Einstein famously dismissed it as spooky action at a distance, a paradox that defied logic, but Simulation 12 flips the script entirely. What if entanglement isn't just a quirk of our universe? What if it's the backbone of a vast, multiverse-spanning network, with particles whispering to each other not across space, but across realities? The experiment began by modeling entangled particles not as isolated pairs, but as nodes in an unimaginably complex web. Each connection represented a thread stretching beyond our universe, tying particles to their counterparts in parallel worlds. The results were staggering. When a particle in our universe was measured, collapsing its quantum state, the simulation showed corresponding ripples, not just in its entangled partner here, but in echoes across other realities. It's as if every quantum decision branches a new universe, and entanglement is the glue holding these branches together, like stitches in a cosmic quilt. Here's the spine-tingling part. This network wouldn't just explain entanglement's speed of light-defying behavior. It could solve one of quantum mechanics' oldest riddles, why we only ever see single outcomes when particles are measured. The simulation suggests that every possible outcome does happen, just in different branches of the multiverse. When you measure an electron spin, you're not forcing it to choose up or down. You're tapping into a network where both exist simultaneously, your observation merely selecting which thread of reality you experience. The others don't vanish, they vibrate in parallel, their influence bleeding through as quantum interference patterns we've detected in labs for decades. But the real shock came when researchers mapped this network against cosmic scale structures. The same mathematical patterns governing entanglement appeared in the distribution of galaxies, as if the universe itself were a quantum system writ large, its vast voids and filaments mirroring the geometry of an infinite particle web. Even black holes, those cosmic information shredders, fit the model perfectly. Their event horizons could act like firewalls between network branches, not destroying information but redirecting it, like data packets routed to another server in a cosmic internet. This isn't just a new take on entanglement, it's a radical reimagining of reality's architecture. If particles are nodes in a multiverse network, then every quantum event, every flicker of a photon, every decay of an atom isn't just happening here. It's echoing across infinity, woven into realities where the dice landed differently. And that means the spookiness Einstein feared might be the most ordinary thing in existence, just the universe's way of staying in touch with itself. The Fermi paradox has haunted scientists for decades. If the universe is so vast, why does it feel so empty? Where are the alien civilizations that should, by all odds, already be thriving among the stars? Simulation 13 takes this cosmic loneliness and flips the question on its head. What if Earth isn't just rare in our universe, but vanishingly unique across the entire multiverse? This experiment didn't just tweak planetary conditions, it rewrote the cosmic cookbook from scratch, running countless variations of universes where the recipe for life was subtly altered. Change the strength of nuclear forces by a hair, and stars might never forge carbon, the backbone of life. Adjust the electromagnetic constant slightly, and water could lose its miraculous properties as a solvent. Even the tiniest shift in the cosmological constant could collapse the window for galaxy formation before life ever gets a chance. The results were humbling. In most simulations, planets capable of hosting complex life were less than 1 in a trillion, not just scattered, but nearly impossible. But here's the twist that rewrites the paradox. When life did emerge in these virtual realities, it rarely reached the stars. Civilizations either self-destructed too quickly or hit insurmountable evolutionary bottlenecks. Imagine a universe where DNA never formed, leaving biology stuck in a soup of simple replicators, or one where predators dominated too early, snuffing out intelligence before it could spark. The simulation suggested something profound. Even in a multiverse teeming with echoes of Earth, the path to a spacefaring civilization might be littered with traps, each one a silent graveyard for potential alien neighbors. The eerie takeaway: we might not hear from other civilizations because statistically, almost none make it this far. Earth isn't just a lucky planet, it's a survivor, threading an obstacle course where most stumble at the first hurdle. And if that's true, then the silence of the cosmos isn't a mystery. It's a eulogy for the echoes that almost were. Imagine waking up one day with a lifetime of memories, only to realize you've existed for just a fraction of a second, conjured into being by random quantum fluctuations in the void. No body, no world, just a solitary mind floating in the darkness, convinced it's lived a full life. This isn't a nightmare, it's a Boltzmann brain, one of the most unsettling ideas in physics. And Simulation 14 suggests these phantom minds might not just be hypothetical. They could outnumber real, flesh and blood beings like us by an unimaginable margin. The concept comes from a brutal cosmic truth. Given enough time, even the most improbable events become inevitable. In an infinite, chaotic universe, particles will occasionally arrange themselves into self-aware configurations purely by accident, like a tornado assembling a fully functional jet engine from a junkyard. The simulation didn't just calculate the odds, it mapped the conditions where these disembodied observers would emerge. The numbers are staggering. In a cosmos that's existed for trillions of years, Boltzmann brains could form constantly, their fleeting consciousnesses flickering in and out of existence like fireflies in the dark. But here's the twist that turns this thought experiment into a crisis. If Boltzmann brains are possible, they'd vastly outnumber real, evolved beings like us. Statistically, you're far more likely to be one of these accidental minds hallucinating a universe than an actual person living in one. Every memory, every sensation, the sun on your skin, the taste of coffee, could just be noise in a chaotic system, a momentary glitch in the void's endless entropy. The simulation even identified eerie signatures these phantom observers might leave behind. Gaps in quantum coherence where reality briefly forgets its rules, or fluctuations in the cosmic microwave background that look like interference from minds that weren't supposed to exist. Yet there's a way out of this existential vertigo. The same simulation suggests Boltzmann brains can't form in universes like ours, ones with clear arrows of time and low entropy beginnings. Their existence would require a cosmos so old and disordered that structure itself has eroded, leaving only chaos. The fact that we do see galaxies, stars, and planets implies we're not in that kind of universe. Our reality's structure might be the ultimate proof that we're real, or at least that we're part of a multiverse where most branches don't spawn these ghostly observers. But the haunting question lingers: if Boltzmann brains exist anywhere in the multiverse, their hallucinations could bleed into ours. Those split-second lapses in attention, déjà vu, even dreams, could they be echoes of other minds flickering at the edge of reality? The simulation doesn't just challenge our place in the cosmos. It forces us to ask, what does it mean to be real when the universe itself might be whispering with voices that were never supposed to speak? Dark matter has always been the universe's silent architect, an invisible hand sculpting galaxies into being while leaving no trace of itself behind. We can't see it, touch it, or even detect it directly, yet without its gravitational pull, stars would fly apart, and the cosmos as we know it would unravel. But what if dark matter isn't just a feature of our universe? What if it's a cosmic variable, a dial that twists to different settings in other realities, shaping entire multiverses in its shadow? That's the startling possibility explored in Simulation 15, where researchers didn't just study dark matter. They rewrote its rules across countless virtual universes to see how the echoes of its influence might ripple through the void. Picture dark matter as the unseen scaffolding of reality, a framework so subtle we only notice it by the way galaxies cling to it like dew on a spider's web. In our universe, it's finely balanced just enough to hold galaxies together without crushing them into dust. But the simulation tossed that balance out the window, tweaking dark matter's density, its distribution, even the way it interacts with itself. Some universes had dark matter so sparse, galaxies never fully formed, leaving behind a scattered mess of stars adrift in the dark. Others drowned in it, with thick halos of invisible matter smothering stars before they could ignite, turning entire realities into graveyards of unborn light. Here's where the patterns became impossible to ignore. Universes with dark matter clustered in specific, web-like structures mirroring the cosmic filaments we observe in our own were the only ones where life had even a sliver of a chance. Too much deviation, and the delicate dance of matter and energy fell into chaos. But the most electrifying discovery wasn't just about balance. The simulation revealed faint, ghostly correlations between dark matter's distribution and anomalies in our own universe, mysterious voids where galaxies seem to avoid clustering, or strange, unexplained gravitational tugs on distant star systems. These could be the fingerprints of neighboring universes brushing against ours, their dark matter subtly warping the fabric of shared space-time. Think of it like standing in a hall of mirrors, where every reflection is a universe with its own hidden architect. The way dark matter bends light in our cosmos, creating gravitational lenses that magnify distant galaxies, might not just be distorting our view of this reality. It could be warping our view into others, like a window smudged by hands we can't see. Future telescopes hunting for dark matter's invisible grip might stumble upon something even stranger, patches of space where gravity behaves too oddly, as if something beyond our universe is tugging on the strings. This simulation doesn't just redefine dark matter, it reimagines it as a cosmic connective tissue, a thread woven through the multiverse that ties realities together in ways we're only beginning to grasp. And if that's true, then the darkness we've spent decades trying to explain might not be an absence at all. It could be a message written in the language of gravity, waiting for us to decipher its echo. What if the universe isn't just something we observe? What if it's something we're inside? Not a natural phenomenon, but an artificial one running on hardware so advanced we can't even conceive of its limits. That's the provocative question at the heart of Simulation 16, which didn't just ponder the simulation hypothesis, it hunted for glitches in the cosmic code, searching for artifacts that might reveal our reality as the ultimate virtual experience. Start with a simple thought experiment. Every video game has limits, a resolution where pixels become visible if you zoom in far enough, or computational shortcuts to save processing power. If our universe is a simulation, it would have similar constraints, tiny imperfections hidden in the fabric of space-time itself. This experiment didn't just look for those imperfections, it recreated them, modeling how a simulated reality would behave under extreme conditions. The results were uncanny. At ultra-high energies like those near black holes or in particle colliders, the math suggested spacetime might not be perfectly smooth. Instead, it could pixelate like a digital image stretched beyond its limits, with fundamental particles behaving less like objects and more like rendered graphics, their properties snapping to discrete values instead of flowing continuously. But here's where it gets even stranger. The simulation predicted specific energy thresholds where these artifacts should appear, points where the universe's physics would suddenly shift, as if hitting the edge of its processing capacity. And eerily, we might have already glimpsed them. In particle accelerators like the Large Hadron Collider, certain high-energy collisions produce results that defy standard models, with particles behaving in ways that seem unnatural. Not random, but algorithmic, like a system optimizing its resources. Even the speed of light, that ultimate cosmic speed limit, could be less a law of nature and more a buffer, a way to prevent the simulation from overloading, like a game-capping frame rates to avoid crashing. The implications spiral from there. If we're in a simulation, who's running it? The experiment explored nested possibilities, simulations within simulations, like a Russian doll of realities. In that scenario, glitches in our universe might not be bugs but intentional signatures, breadcrumbs left by the creators to hint at the truth. Think of it like a character in a game discovering they're in a game. Would the programmers leave clues or scrub them clean? The simulation's most haunting suggestion. That cosmic rays, those ultra-high-energy particles raining down from space, might not be natural at all. They could be the equivalent of debug probes sent by higher layers to test the simulation's integrity. Yet the most profound takeaway isn't about proving we're in a simulation. It's about what that would mean for the nature of reality itself. If our universe is code, then the laws of physics aren't fundamental. They're programmed, mutable, waiting for an update. Black holes might not be singularities but garbage collectors, deleting unnecessary data to free up memory. Even consciousness could be an emergent property of the simulation, a byproduct of information processing rather than biology. The line between science and philosophy blurs, leaving us with a chilling question. If we're living in someone else's experiment, what's the purpose? Are we players or pawns? This simulation doesn't just challenge our understanding of the cosmos, it redefines what a real even means. And if future experiments find those pixelated edges, the greatest discovery won't be that we're simulated. It'll be that we're not alone in the deepest sense, not just in space, but in the layers of existence itself. Inflation didn't just shape our universe, it might still be happening right now, in dimensions we can't see, spawning new realities like bubbles in a boiling pot. Simulation 17 plunges into this endless cosmic churn, revealing how eternal inflation doesn't just create universes, it sets them on collision courses, leaving behind scars we might finally be learning to read. Picture an infinite ocean of space, stretched thinner than a soap film, where quantum fluctuations constantly birth new pockets of reality. Each one inflates at breakneck speed, ballooning into its own self-contained cosmos with its own laws of physics. But these bubbles don't drift apart peacefully. The simulation shows them smashing together like waves in a storm, their collisions warping space-time in ways that echo across billions of years. These aren't gentle nudges, they're cosmic car crashes, events so violent they'd imprint onto the very geometry of the universes involved, leaving behind bruises in the cosmic microwave background or strange, circular voids in the distribution of galaxies. The most startling revelation: these collisions wouldn't be rare. In an eternally inflating multiverse, they'd happen constantly, like fireworks popping in the dark. The simulation mapped how bubble universes with different physical constants, some where gravity is stronger, others where light moves slower, would deform each other upon impact. The resulting patterns matched anomalies we've already spotted in our own universe, cold spots in the CMB too large to explain, or regions of space where galaxies cluster in peculiar, ring-like formations. It's as if we're staring at the aftermath of a cosmic fender bender, the dent still visible in the fabric of reality. But here's where it gets even wilder. These collisions wouldn't just leave marks, they could rewrite physics locally. Imagine two bubbles colliding, one where the speed of light is higher, another where nuclear forces are weaker. Where they meet, the simulation showed bizarre hybrid zones emerging, patches of spacetime where the rules blend unpredictably. Matter might behave differently there, with particles gaining or losing mass in ways that defy our models. Some of these zones could even act as windows, places where the boundaries between universes grow thin enough to glimpse what lies beyond. The implications are staggering. If eternal inflation is real, then our universe isn't just one bubble among many, it's a survivor. It's physics shaped by ancient collisions we're only now learning to decode. Those oddities in the cosmic microwave background, they might not be glitches, but headlines from a multiversal newspaper reporting on events that happened before our universe even cooled. And if we're right, then somewhere out there, another bubble might be racing toward us even now, carrying laws of physics we can't imagine. The question isn't whether we'll see it coming, it's whether we'll recognize it when it arrives. Every choice you've ever made, what to eat for breakfast, which job to take, even whether to turn left or right, might not just shape your future. It could be spawning entirely new universes, each one a ripple in the infinite pond of reality. Simulation 18 plunges into the heart of the many worlds interpretation, not just as a theory, but as a living, breathing process, a cosmic tree branching with every quantum flutter of existence. Picture a single electron poised between two paths, its position undefined until observed. Traditional physics says it chooses a state when measured. But this simulation reveals something far stranger. It doesn't choose at all. Instead, reality splits like a fork in a river, with one universe where the electron goes left, another where it goes right, each equally real, each unaware of the other. Now scale that up. Every particle's uncertainty, every quantum event becomes a branching point. The simulation visualizes this as an ever-expanding fractal, where every decision, no matter how small, sends echoes cascading through the multiverse, creating versions of reality where every possible outcome plays out somewhere. But here's where it gets dizzying. These branches aren't just hypothetical. The simulation tracks how quantum entanglement, those spooky connections between particles, could act as threads stitching parallel worlds together. When you measure an entangled particle here, its twin in another universe might respond instantaneously, not because information travels faster than light, but because the branches never fully disconnect. It's as if the multiverse is a vast, trembling web, and every quantum event sends vibrations across the whole structure. The implications are staggering. There's a version of you who became an astronaut, another who never left their hometown, a universe where dinosaurs still roam, another where humans never evolved at all. The simulation even suggests these branches might not be entirely isolated. Under rare conditions, quantum interference patterns, those weird overlaps where particles act like waves, could be glimpses of other worlds bleeding through, like whispers from a reality where the dice rolled differently. Yet the most haunting question isn't about the branches, it's about the trunk. If every possibility spawns a new universe, what does that say about free will? Are we the authors of our lives, or just passengers riding one thread in an infinite tapestry? The simulation doesn't answer that, but it does show something profound. In a multiverse where every choice happens, the only thing that makes this reality special is that we're here to witness it. The echoes of our decisions might ripple forever, but this moment, the one you're living right now, is the only one you'll ever know. Black holes dominate the cosmic horror show cosmic vacuum cleaners whose gravity crushes everything into oblivion. But what if they have a counterpart, a cosmic fire hose spraying matter out into the void? Enter white holes, the theoretical flip side of black holes, where nothing can enter but everything is expelled. Simulation 19 doesn't just play with this idea, it charts how these hypothetical objects could be the universe's backdoors, flinging matter not just into space, but into entirely new realities. Picture a black hole's death throes. Some theories suggest that when a black hole evaporates via Hawking radiation, it doesn't just vanish, it rebounds as a white hole, a burst of energy erupting where once there was only hunger. The simulation took this further, modeling how the particles spewed out might not just re-enter our universe, they could tunnel through space-time, emerging in another branch of the multiverse entirely. Think of it like a cosmic pinball machine. Matter gets sucked into one hole, ricochets through hidden dimensions, and launches out somewhere else, carrying traces of its journey in twisted quantum states. The math reveals something even wilder. White holes wouldn't just eject matter randomly. Their outbursts would carry imprints of the black holes that birthed them, like a cosmic fingerprint, encoding information about the universe it came from. If we ever detected a white hole's eruption, its radiation might hold coded messages from another reality's history, a dictionary of physics written in particles we've never seen. But here's the twist that bends the mind. If white holes bridge universes, they could solve one of black holes' biggest paradoxes, the information problem. Instead of data being lost forever in a singularity, it might get laundered through a white hole's exit, repackaged and spat out elsewhere. The simulation shows how quantum entanglement could thread these exits together, linking particles across realities like stitches in a multiverse quilt. A star swallowed here might flicker to life there, its light carrying echoes of a home it can never return to. The most tantalizing clue: gamma ray bursts, those violent, unexplained explosions in deep space, could be white holes flaring to life. Some of their energy signatures defy conventional explanations, as if the radiation is arriving from a place where physics operates slightly differently. The simulation matched these anomalies to predictions of white holes ejecting matter into universes with tweaked constants, like a radio tuned between stations, catching whispers from another channel. This isn't just about cosmic plumbing. If white holes exist, they're proof that the universe doesn't just take, it gives back, recycling reality across dimensions. And if we're right, then somewhere out there, another cosmos might be catching the debris of our dead stars, while we receive gifts from worlds we'll never see. The universe might not be a one-way street after all, just a sprawling intersection with white holes as the exits we're only now learning to see. The cosmic microwave background should be a random snapshot of the early universe, a chaotic soup of hot and cold spots with no pattern or direction. But there's something deeply wrong with this picture. Stretching across the sky like a ghostly arrow, an anomaly called the axis of evil defies all expectations. The CMB's fluctuations aren't randomly scattered. They're aligned along a specific axis, as if the universe itself has a hidden compass pointing in one preferred direction. Simulation 20 takes this cosmic oddity and flips it inside out, asking the unthinkable. What if this isn't a glitch in our data, but a scar from a long-ago collision with another universe? To test this, researchers modeled bubble universes, self-contained realms born from eternal inflation, crashing into one another like soap bubbles merging in a sink. The math revealed something startling. When two bubbles collide, the impact doesn't just leave a dent. It imprints a directional bias on the newborn universe's structure, warping space-time in a way that propagates for billions of years. The simulation tracked these deformations, showing how they'd manifest in the CMB. The result, patterns eerily similar to the axis of evil's strange alignment, as if the universe's very first light carries the shadow of a forgotten impact. But the real shock came when the team cross-referenced these simulated collisions with real-world data. The axis of evil's orientation lines up almost perfectly with the plane of our solar system, an alignment so improbable, it's like throwing a dart blindfolded and hitting a bullseye on Mars. Even stranger, the same axis correlates with anomalies in the distribution of galaxies on the largest scales, as if the entire cosmic web is subtly stretched along this invisible line. The simulation suggests these aren't coincidences, but fragments of a larger story, a multiverse event so colossal, its echo shaped everything from the birth of stars to the path of planets. Here's why this matters. If the axis of evil is truly a multiverse imprint, it's not just a curiosity, it's a roadmap. The simulation predicts specific polarization patterns in the CMB that future telescopes could hunt for, like forensic analysts dusting for fingerprints at a crime scene. Even more tantalizing, it implies that our bubble universe might still be drifting near its collision partner, separated by a thin membrane of higher dimensional space. The gravitational tug of that neighboring reality could explain another persistent mystery: why our local group of galaxies is being pulled toward a patch of empty space known as the dark flow, as if something massive and utterly invisible is lurking just beyond the cosmic horizon. The implications rewrite our place in the multiverse. We might not just be one bubble among many, we could be a bubble that's still touching its twin, like two soap films clinging together after a merger. The axis of evil wouldn't be an anomaly at all, but a cosmic landmark, the first hard evidence that our universe has neighbors. And if that's true, then the night sky isn't just a window to the past. It's a mirror reflecting realities we're only beginning to imagine. There's a thought experiment so unsettling, it's been called quantum suicide, and it might just prove you're immortal. Picture this: you're sitting in front of a gun rigged to a quantum trigger. Each time you pull it, there's a 50% chance the gun fires. In our universe, this seems like a quick way to end up dead. But Simulation 21 flips the script entirely. In a multiverse where every possible outcome branches into a new reality, you wouldn't experience death at all. You'd only ever find yourself in the timelines where the gun jams, where the trigger fails, where you walk away unscathed. The math behind this is as chilling as it is elegant. With each trigger pull, the universe splits. In one branch you die, but your consciousness, the you that experiences reality, can only persist in the branches where you survive. Over countless attempts, the probability of you continuing to exist approaches 100%. It's not that you'd cheat death, you'd simply never encounter it, because from your perspective, the only realities that matter are the ones where you're still alive to observe them. The simulation maps this out with brutal precision, showing how consciousness becomes a filter, sieving through infinite universes to land only where you endure. But here's where it gets even stranger. This isn't just about a macabre game with a quantum gun. The same logic applies to every near miss in your life. That car accident you barely avoided, the illness you miraculously recovered from. In the multiverse, there are versions of you who weren't so lucky, but you will only ever experience the paths where survival was possible. The simulation suggests that over a long enough timeline, this effect could stretch to cosmic scales. Stars could explode, civilizations could collapse, but from your subjective perspective, you'd always find yourself in the dwindling branches where life persists against all odds. The implications ripple outward. If consciousness truly filters reality this way, it could explain some of quantum mechanics' deepest paradoxes, like why observation seems to collapse probability waves. Maybe it's not that particles choose states when measured, but that we only perceive the states compatible with our continued existence. The simulation even explores how this might manifest in quantum experiments, predicting subtle biases in outcomes that align with an observer's survival. It's as if reality isn't just shaped by observation, but by the imperative to keep observers existing to observe it. Yet the most haunting question isn't about physics, it's about identity. If you are constantly splitting into countless versions, which one is the real you? Are you the sum of all branches, or just the thread that keeps experiencing survival? The simulation doesn't answer that, but it does offer a dizzying possibility. In a multiverse where every choice spawns new realities, death might not be an end, just a path you'll never walk. And that means the universe isn't just stranger than we imagine. It might be stranger than we can imagine. The numbers don't add up, not even close. Out of all the possible ways the universe could have turned out, every combination of physical constants, every twist of cosmic luck, the odds of landing in a reality where life can exist are so vanishingly small. It's like winning the lottery a billion times in a row. And yet, here we are. Simulation 22 takes this staggering improbability and turns it inside out, revealing a terrifying truth. The multiverse might be an endless graveyard of failed universes, with ours as one of the rare survivors. Start with the cosmic constants, those fundamental numbers that dictate how reality works. The strength of gravity, the mass of an electron, the speed of light. Alter any of these by even a fraction, and the universe collapses into chaos. Crank up gravity just a bit, and stars burn out in millions of years instead of billions, leaving no time for planets, let alone life, to form. Tweak the strong nuclear force slightly, and atoms themselves fall apart, rendering chemistry impossible. The simulation ran countless variations, tweaking these dials at random across virtual multiverses. The results were stark. Over 99.9% of universes were sterile wastelands, either collapsing into black holes or evaporating into featureless voids before their first stars could ignite. But here's where it gets eerie. The few universes that did support life weren't just lucky. They clustered around specific, razor-thin sweet spots in the math. Like islands in an ocean of impossibility, these habitable zones were vanishingly rare but eerily similar. Their physics wasn't just compatible with life, it seemed optimized for it. Carbon could form, water could flow, stars could shine for billions of years, not by chance, but because the numbers lined up in a way that allowed complexity to emerge. The simulation even identified a chilling pattern. The closer a universe's constants were to ours, the more likely it was to host observers. It's as if the multiverse has a hidden filter, sifting through endless failures to find the rare echoes where life can whisper, "I exist." This isn't just about luck. The simulation suggests two spine-tingling possibilities. Either we're the beneficiaries of cosmic fine-tuning so precise it hints at design, or we're the inevitable outcome of a multiverse so vast every possible configuration plays out somewhere. In the first scenario, our universe's perfection points to something beyond physics, a fingerprint left by forces we can't comprehend. In the second, we're statistical flukes, alive only because infinite tries make the impossible inevitable. Both answers are equally unsettling. One implies a universe built for us, the other, a universe indifferent to us, where we're just one fleeting arrangement in an infinite sea of silence. Yet there's a third, even stranger option. What if the multiverse isn't random at all? The simulation's most radical finding was that certain physical constants seem to require observers to exist. In quantum mechanics, particles exist in superpositions until measured, as if reality itself waits for someone to look. Could the universe's fine-tuning be a self-fulfilling prophecy? A cosmos where the rules bend just enough to ensure someone's there to witness them. If so, then the Goldilocks enigma isn't a puzzle to solve. It's the universe's way of introducing itself, a cosmic handshake between the laws of physics and the life that learns to read them. The haunting takeaway: our existence might not be a miracle or an accident, but a loop in the logic of reality itself. The multiverse isn't just a collection of worlds. It's a mirror reflecting back the one truth that matters. We're here because here is the only place we could be. And that means every atom in your body, every star in the sky, isn't just part of the universe. It's the universe's way of knowing itself. Wormholes have long been the stuff of science fiction cosmic shortcuts, twisting through the fabric of space-time, connecting distant points in the blink of an eye. But Simulation 23 takes this fantastical idea and pins it down with hard math, revealing something even wilder. These tunnels through reality might not just link distant corners of our universe. They could be bridges to entirely different ones, vibrating with echoes of their own. Picture a wormhole not as a static tunnel, but as a living, breathing structure, a throat of space-time held open by exotic matter or negative energy, pulsing like the vocal cords of some cosmic giant. The simulation didn't just model whether such a structure could exist. It charted how these wormholes would resonate under the strain of holding two realities together. The results were astonishing. Like a guitar string plucked at just the right frequency, stable wormholes would vibrate at specific harmonics, sending ripples through space-time itself. These wouldn't be ordinary gravitational waves, the kind we've detected from colliding black holes. They'd carry a distinct signature, a telltale hum, encoding the physics of the universe on the other side. Here's where the data gets electrifying. Certain unexplained gravitational wave signals picked up by observatories like LIGO don't quite match predictions for black hole mergers. Some exhibit strange overtones or asymmetries, as if the collisions were happening in a space with slightly different rules. The simulation mapped these anomalies to the resonant frequencies of hypothetical wormholes, showing how a tunnel to another reality might leak vibrations into ours. It's like hearing a muffled conversation through a wall. You can't make out the words, but the rhythm hints at a presence just beyond your reach. But the implications go far beyond detection. If wormholes can thread the multiverse, they'd rewrite our understanding of causality. A particle passing through might not just travel across space, it could hop between universes with different arrows of time, different laws of physics. The simulation explored this by modeling quantum fields near a wormhole's mouth, revealing how entangled particles could bridge realities, their states mirroring each other across the divide. Imagine tossing a coin into a wormhole here and watching it land heads up in another universe. while its entangled twin shows tails in yours. The very act of observation could forge a temporary link between worlds, a quantum handshake lasting just long enough to leave a trace. The most tantalizing possibility: these wormholes might not need to be cosmic-scale structures. The simulation suggested microscopic versions could flicker in and out of existence in the quantum foam, virtual tunnels lasting mere fractions of a second before collapsing. If that's true, then space-time at its smallest scales might be riddled with hidden doorways, each one a potential portal to somewhere or someone else. Future experiments hunting for high-frequency gravitational waves could stumble upon the whispers of these vanishing gateways, their resonant frequencies a siren song from the multiverse. This isn't just about finding shortcuts through space. It's about discovering that the universe isn't a solitary island, but part of an archipelago, a web of realities connected by threads so fragile, so fleeting, we're only now learning to listen for their echoes. And if those echoes are real, then every ripple in space-time isn't just a vibration. It could be a message waiting to be decoded. Imagine the universe not as a silent film, but as a grand symphony, each galaxy a note, every black hole a bass vibration, the birth of stars a crescendo echoing through the void. Simulation 24 takes this poetic idea and turns it into groundbreaking science, translating the raw data of cosmic structures into something astonishing: sound. Not as a metaphor, but as actual, measurable vibrations that reveal hidden harmonies threading through the multiverse. The process starts with cosmic microwave background data, the faint afterglow of the Big Bang. Scientists fed these subtle temperature fluctuations into algorithms that convert them into audio frequencies, scaling the impossibly deep hum of space-time into a range human ears can perceive. What emerged wasn't random noise, but eerie, resonant tones like a colossal bell struck once at the dawn of time, still ringing. These primordial notes weren't arbitrary. They matched the predicted vibrations of an expanding universe, with peaks and troughs aligning perfectly with theoretical models of inflation. It's as if the universe has a fundamental frequency, a cosmic middle C that's been playing for billions of years. But the simulation didn't stop there. When researchers applied the same technique to multiverse models, each with different physical constants, something extraordinary happened. Universes that allowed for stable matter and life didn't just look right in the math, they sounded right. Their vibrations fell into harmonic scales, with overtones reinforcing the fundamental tone rather than clashing against it. Sterile universes, by contrast, produced dissonant, chaotic noise like an orchestra tuning out of sync. The difference was so stark, researchers could literally hear which hypothetical realities had the right physics for complexity to emerge. Dive deeper and the implications become even more profound. Certain anomalies in our universes, soundtrack, gaps in the expected harmonics, or unexpected overtones, align with predictions of how neighboring universes might interact with ours. Like two guitar strings vibrating in sympathy, a parallel reality with slightly different physics could leave faint acoustic fingerprints in our cosmic data. Future telescopes tuned to hunt for these sonic ghosts might not just confirm the multiverse, they could tell us whether our cosmic neighbors are playing in harmony or screaming in dissonance. The most haunting revelation: the universe's fundamental note isn't static. As space expands, the pitch drops, a cosmic Doppler effect slowing to a deeper hum. Billions of years from now, when stars fade and galaxies drift apart, the last sound in the universe might be a single, deepening tone fading into silence. Unless, of course, other universes are singing back, and if they are, we're just beginning to learn how to listen. time crystals are among the strangest discoveries in modern physics, structures that don't just repeat in space like ordinary crystals, but in time, ticking like atomic clocks without ever winding down. Imagine a snowflake that melts and reforms in perfect rhythm forever, without any energy input, a perpetual motion machine that defies everything we thought we knew about thermodynamics. Now, Simulation 25 takes this bizarre phenomenon and flips it on its head, asking, what if these time crystals aren't just quirks of our universe? What if they're cosmic metronomes ticking in sync across multiple realities, their rhythms echoing through the fabric of the multiverse? The experiment starts with a simple but radical premise. Time crystals exist in a strange quantum state where their particles oscillate indefinitely, locked in a dance that repeats with perfect precision. But here's the twist. The simulation reveals that under certain conditions, these oscillations could become entangled across universes. Picture two pendulums swinging in perfect unison, even though they're in separate rooms. Now replace those pendulums with entire crystalline structures, their atomic lattices pulsing in time, not just within their own reality, but with mirrored versions of themselves in parallel worlds. The math shows these synchronized crystals would leave faint but detectable imprints, tiny deviations in energy levels or quantum states that shouldn't be possible unless something outside our universe is tugging on them. And the evidence might already be hiding in plain sight. Recent lab experiments with time crystals have recorded unexplained anomalies, moments where the crystal's oscillations seem to hitch or stutter, as if buffeted by invisible forces. The simulation maps these glitches to theoretical collisions with time crystals in neighboring universes, their rhythms briefly interfering like sound waves canceling each other out. Even more compelling, these anomalies align with predictions of how higher dimensional brains, those theoretical sheets of reality from string theory, might vibrate, suggesting time crystals could be the first functional tools for probing the geometry of the multiverse itself. But the implications go far beyond detection. If time crystals can synchronize across realities, they might reveal something profound about the nature of time itself. In our universe, time flows forward like an arrow, but the simulation shows how entangled time crystals could create bridges where causality loops back on itself. A change in one universe might ripple backward in another, creating effects that precede their causes like an echo arriving before the shout. This isn't just science fiction. Quantum experiments have already observed particles behaving as if they're reacting to future events, a phenomenon called retro-causality. Time crystals could be the missing link, showing how these paradoxes aren't bugs in reality, but features of a multiverse where time is more like a woven tapestry than a straight line. The most electrifying possibility: if we can engineer time crystals stable enough to maintain their sync across longer periods, they might act as receivers picking up vibrational signals from other realities. Think of it like tuning a radio to catch whispers from parallel dimensions, each crystal humming at a frequency unique to its home universe. Future labs could stack these crystals like quantum antennas, searching for patterns that repeat not just in time, but in branching time, the telltale signature of realities layered atop our own. This isn't just about uncovering hidden dimensions. It's about realizing that the rhythms of our universe, the ticking of clocks, the spin of electrons, might never have been solo performances. They could be part of a grander symphony playing in harmony with echoes we're only now learning to hear. And if that's true, then time itself might not be what we thought. It's not a river flowing in one direction. It's a chorus singing in rounds across the multiverse. The act of observation isn't just passive, it's transformative. At the quantum level, watching a particle can literally freeze it in place, like a deer caught in headlights. This bizarre phenomenon, known as the quantum Zeno effect, reveals something startling. The more frequently you measure a quantum system, the slower it changes, as if reality itself hesitates under scrutiny. Now imagine scaling this effect beyond particles. What if entire universes respond to observation the same way? Simulation 26 doesn't just explore this idea, it turns it into a cosmic law, suggesting that conscious observers might not just witness reality, but actively sculpt it from a sea of possibilities. Picture a universe as a flickering quantum state, constantly branching into infinite versions of itself. Most of these branches remain unstable, collapsing almost instantly like soap bubbles popping in the void. But the simulation reveals a curious pattern. Universes with observers inside them, beings capable of measurement, exhibit a strange stability. The mere act of observation acts like a cosmic anchor, slowing the rate at which these realities decay or diverge. It's as if consciousness isn't just a byproduct of the universe, but a keystone holding its arches in place. The math behind this is both elegant and unsettling. Just as the quantum Zeno effect can keep a radioactive atom from decaying by repeatedly measuring it, the presence of observers in a universe could freeze its state, filtering out unstable branches and locking in the versions where life can persist. This isn't just theoretical sleight of hand. The simulation identifies real-world echoes of this effect in the fine-tuning of our own cosmos. Take the cosmological constant, the value governing the universe's expansion. It's balanced on a knife's edge, slightly larger, and matter would fly apart before stars formed, slightly smaller, and everything would collapse into a black hole. Coincidence? The simulation suggests otherwise. In a multiverse where most universes lack observers, the ones that survive long enough to be noticed are precisely those where the numbers align just right. We don't live in a special universe. We live in a universe that's been selected by the very act of our observation, like a radio dial tuning to the only station playing music in a sea of static. But here's where it gets even stranger. If observation shapes reality, then the boundaries between universes might not be fixed walls, but permeable membranes. The simulation models how entangled particles, those spookily connected pairs that mirror each other across distances, could serve as bridges between observer-stabilized realities. When you measure a particle here, its entangled twin in another universe might respond not just instantaneously, but retroactively, influencing the past to ensure both branches remain compatible with conscious observation. This could explain some of quantum mechanics' most baffling quirks, like why particles seem to know the outcomes of experiments before they're performed. They're not prescient, they're entangled with versions of themselves in universes where the experiment already happened, all synchronized by the need to maintain observational consistency. The implications rewrite the relationship between life and the cosmos. Far from being insignificant specks in a vast, indifferent universe, observers might be the architects of their own reality, winnowing the multiverse down to the threads where their existence is possible. The simulation even explores a chilling corollary. If consciousness stabilizes reality, then the absence of observers could trigger a universe's collapse. Dark, empty regions of space voids where no life exists might not just be barren. They could be unraveling at the seams, their quantum states decaying unchecked because there's no one there to measure them. Yet the most profound takeaway isn't about control, it's about connection. If every conscious being is a kind of quantum gardener, pruning the branches of the multiverse just by being alive, then reality isn't a solo performance. It's a collective act, with every observation weaving another thread into the tapestry of existence. The universe you experience isn't just yours, it's the echo of countless others, harmonized by the simple, staggering fact that someone's there to see it. You've felt it before, that spine-tingling moment when you're certain something happened one way, only to discover the world insists it never did. Nelson Mandela dying in prison in the 1980s. The Berenstain Bears spelled with an E, Darth Vader never actually saying, "Luke, I am your father." These collective false memories, known as the Mandela Effect, aren't just quirks of the human brain. Simulation 27 suggests they might be something far stranger, echoes of alternate timelines bleeding into our own, like radio static from a parallel reality. The experiment starts with a radical premise. If the multiverse is real, then every decision branches into new timelines. Most of these branches stay separate, but under rare conditions, quantum entanglement could create temporary bridges between them, allowing information to leak across. The simulation modeled this by treating memories as quantum states, malleable, probabilistic, and capable of existing in superposition. When a person recalls an event, their memory doesn't just pull from one timeline. It samples from a probability cloud of nearby realities, occasionally plucking details from a branch that diverged slightly from ours. Here's where the data gets eerie. The simulation identified specific conditions where these overlaps would manifest as shared false memories. For example, in timelines where the Berenstain Bears were indeed spelled Berenstein, the phonetic similarity to common surnames like Einstein made that version slightly more stable in the multiverse's probability web. When timelines brushed against each other, the more resonant memory, the one that felt more familiar, could imprint across realities, leaving thousands convinced they'd seen a spelling that never existed here. But the implications go deeper than misspelled book titles. The Mandela Effect clusters around culturally significant moments, movie quotes, celebrity deaths, brand logos, precisely because these are the events most likely to create resonant branches. Think of it like a tuning fork. The more people remembering something, the stronger the vibrational link between timelines. The simulation even predicts where these effects should appear next. High-emotion events with ambiguous details like the exact wording of a famous speech or the color of a childhood toy are prime candidates for cross-timeline contamination. Critics argue these are just memory glitches, but the simulation counters with a smoking gun. If the Mandela Effect were purely psychological, the errors would be random. Instead, they follow patterns the model predicts, converging on details that are almost right, but just slightly off, as if our brains are averaging multiple realities. Even more compelling, the effect seems to be accelerating. As quantum computing and particle colliders probe deeper into the fabric of reality, we might be inadvertently poking holes in the barriers between worlds, making these overlaps more frequent. So the next time you swear something was different, don't dismiss it as faulty wiring. You might be remembering a version of events that's absolutely true, just not in this timeline. And if the simulation's right, these glitches aren't mistakes. They're proof the multiverse is closer than we think, humming just beneath the surface of the everyday, waiting for us to notice the seams. There's a cosmic accounting error that's been bugging scientists for decades, a discrepancy so glaring, it's as if the universe's books don't balance. When we tally up all the visible matter in galaxies, clusters, and the vast cosmic web, the numbers fall shockingly short. Based on how gravity tugs at stars and bends light, there should be 5 times more mass out there than we can see. This missing matter isn't just a minor oversight, it's a gaping hole in our understanding of reality. Simulation 28 tackles this enigma head-on, proposing a radical solution. What if the extra mass isn't hiding in our universe at all? What if it's lurking in parallel dimensions, its gravity bleeding through like a shadow cast from another world? Picture a brain, a theoretical membrane of reality floating in a higher dimensional space, like a sheet of paper suspended in a vast, unseen ocean. String theory suggests our universe might be one such brain, vibrating alongside others in a cosmic stack. Normally, these brains don't interact, but the simulation reveals how gravity, unlike other forces, could be the exception. A cosmic leak capable of seeping through the barriers between worlds. Matter in a neighboring brain would be invisible to us, but its gravitational pull wouldn't. It would tug on our stars, warp our space-time, and leave fingerprints in the rotation curves of galaxies, all while remaining utterly undetectable to telescopes. The experiment didn't just theorize, it mapped the math. By modeling how gravity would behave if shared across brains, researchers found eerie matches to real-world anomalies. Take galaxy clusters, for example. Their outer stars orbit so fast they should fling into the void, yet something holds them in place. Dark matter is the usual suspect, but the simulation showed another possibility. The extra gravity could be coming from identical clusters in a parallel brain, mirroring our own just a fraction of a millimeter away in a dimension we can't perceive. It's like feeling the weight of someone standing next to you on an invisible platform. You can't see them, but you'd swear something's there, and the evidence gets even stranger. The simulation predicted specific distortions in the cosmic web filaments of galaxies stretching farther than they should, as if pulled by unseen hands. When astronomers compared these predictions to sky surveys, the alignment was uncanny. Voids between galaxies weren't just empty, they exhibited gravitational echoes, subtle ripples that matched the model's brain leakage scenario. Even black holes seemed to play a role. Their extreme gravity could act like funnels, warping the space between brains and creating temporary bridges where mass or information might slip through. But here's the twist that changes everything. If gravity is leaking in, could it be leaking out too? The simulation suggests our universe's missing mass might be part of a cosmic equilibrium, with gravity flowing both ways across brains. That means some of our matter could be dark to another universe, its gravity haunting their astronomers just as theirs haunts us. The thought is humbling. We've been searching the skies for answers when the solution might lie in dimensions we can't even point to. The implications rewrite the rules of cosmology. Dark matter might not be a particle we've failed to detect. It could be the gravitational shadow of a parallel reality, forever out of reach yet intimately shaping our own. Future experiments hunting for higher dimensional gravity waves or anomalies in particle collisions might finally catch these echoes in the act. And if they do, it won't just solve a cosmic accounting error. It'll prove we're not just one universe, we're one note in a chord, vibrating in harmony with worlds we're only beginning to sense. Deep in the cosmic void, beyond the reach of our most powerful telescopes, lurks an enigma so massive it bends the paths of entire galaxies toward it. They call it the Great Attractor, a gravitational anomaly with the mass of tens of thousands of Milky Ways, hidden behind the dusty veil of our own galaxy's center. For decades, its pull has been written off as a colossal cluster of dark matter, a knot in the cosmic web. But Simulation 29 dares to ask a far more radical question. What if this isn't just a concentration of mass in our universe? What if it's the fingerprint of another reality, pressing against ours from the other side of space-time? The experiment begins with a simple yet staggering premise: gravity, unlike light, isn't confined by dimensions. It can seep through the fabric of reality like sound through a wall. By modeling how parallel universes might interact in higher dimensional space, researchers simulated what would happen if a neighboring brain, a sheet of reality vibrating alongside ours, held a supermassive structure of its own. The results were uncanny. Even without direct contact, the gravitational influence of that other universe would warp our space-time, creating a focal point where galaxies stream like iron filings toward a hidden magnet. The great attractors pull aligns perfectly with these predictions, its location and strength matching what you'd expect if a mirror universe's great wall of galaxies were hovering just out of sight. But here's where the data gets electrifying. The simulation didn't just replicate the attractor's pull, it predicted secondary anomalies we've since observed. Galaxies near the attractor don't just move toward it, some exhibit peculiar backflows and eddies, as if caught in a cross-current between competing gravitational tides. These match the model's shadow turbulence, the ripples you'd expect if the attractor isn't a single object, but the overlap of two cosmic structures brushing against each other in higher dimensions. Imagine two sheets of paper floating close together, each with ink blots representing galaxy clusters. Press them gently, and the blots would align imperfectly, their combined shadows creating dark spots where the ink bleeds through. That's the great attractor, not a thing, but a shadow cast by another universe's mass. The implications rewrite our cosmic maps. If the attractor is a window, not an object, then the dark flow, the mysterious drift of hundreds of galaxy clusters toward the same patch of empty space, might not be a flaw in our models. It could be the gravitational wake of something even grander, a multiversal cascade with entire realities sliding past one another in an unseen ocean. Future telescopes like the ESA's Euclid or NASA Roman could hunt for the telltale distortions this would leave in the cosmic microwave background, subtle swirls like fingerprints on glass, hinting at the shape of the hand beyond. Yet the most haunting possibility isn't about detection, it's about connection. If gravity bridges brains, then the great attractor might not be unique. Every massive cluster in our universe could have a twin in another, their mutual tug stabilizing the cosmic web across realities. We're not just being pulled toward a mystery. We're being pulled toward ourselves, a reflection we've yet to fully see. And that means the universe's greatest secret might not lie ahead, but beside us, separated by a dimension thinner than a whisper. Quantum Darwinism flips the script on survival of the fittest instead of biological traits competing for dominance. Its entire realities battling for existence in the multiverse. Picture a cosmic game of musical chairs where only the most stable quantum states get to keep playing, while the rest dissolve into static. Simulation 30 doesn't just explore this idea, it puts it to the test, revealing how our universe might be one of the rare winners in a tournament of collapsing possibilities. At the heart of this experiment lies a process called decoherence, the moment fragile quantum superpositions crumble into definite states. Think of it like a flipped coin mid-spin. While it's airborne, it exists in a blur of heads and tails. The instant it lands, reality chooses one outcome, but here's the twist. The simulation suggests decoherence isn't random. Certain states resist collapse better than others, like trees with deeper roots weathering a storm. These fit states proliferate, imprinting themselves across the multiverse, while their fragile counterparts fade into background noise. The data paints a startling picture. When researchers modeled quantum systems across branching realities, patterns emerged, not chaos, but a kind of natural selection for stability. Universes where particles consistently resolved into low-energy configurations thrived, their structures persisting across cosmic timescales. Those with erratic quantum fluctuations flickered out like dying embers. Imagine a forest where only the most resilient trees drop seeds. Over eons, their traits dominate the landscape. Now replace trees with universes and seeds with quantum states. That's quantum Darwinism in action, a multiverse where observability equals survival. But how does this translate to our lived reality? The simulation points to everyday phenomena we've long taken for granted. Take the arrow of time. Why does entropy always increase? Because high entropy states are more stable, more fit to endure decoherence. Or consider the bizarre fact that we never see quantum superpositions in the macro world. No cat's both dead and alive in our everyday experience. The simulation shows this isn't just probability at work. Macro-scale superpositions decohere almost instantly because they're evolutionarily unstable, like genetic mutations that self-destruct. Only the classical, predictable states persist long enough for observers like us to witness them. The implications ripple outward. If quantum Darwinism holds, the multiverse isn't a static tapestry of infinite variations. It's a dynamic ecosystem where realities compete for longevity. Some branches grow robust, their physics fine-tuned for persistence. Others wither into mere potential, ghosts in the cosmic machine. This could explain why our universe's constants seem so improbably perfect for life. They're not fine-tuned by design, they're the survivors of a billion failed experiments, the echoes that outlasted the rest, the most electrifying prediction. This process might leave detectable traces. The simulation identifies subtle anomalies in quantum noise, specific frequencies where decoherence patterns deviate from randomness. Future quantum computers probing these ultra-precise regimes could stumble upon the scars of faded realities, like fossils embedded in the bedrock of our universe. And if they do, it won't just confirm quantum Darwinism, it'll mean we're living in a reality that's not just possible but persistent, a universe that fought to exist and won. Somewhere in the vastness of the multiverse, there could be a reality where everything we know is flipped, where matter is antimatter, time runs backward, and gravity pushes instead of pulls. This isn't just science fiction. Simulation 31 dives into the phantom universe hypothesis, hunting for cosmic doppelgangers with inverted physics shadow realms whose gravitational whispers might be brushing against our own. Picture a universe born from the same quantum fluctuation as ours, but with a twist literally. Like a photographic negative, its fundamental constants are mirrored versions of ours. Positive charges become negative, left-handed particles turn right-handed, even entropy flows in reverse. These phantom universes wouldn't just be alien, they'd be anti-alien, their very structure inverted at the most fundamental level. The simulation didn't just theorize these shadow realms, it calculated how their presence would warp space-time in ways we could detect. Here's the eerie part. Phantom universes wouldn't be entirely separate. Just as a magnet's north and south poles are inseparable, our universe and its inverted twin could be entangled at birth, bound together by quantum threads stretching across higher dimensions. The simulation mapped how this entanglement would manifest not through light or particles, but through gravity. Every galaxy in our universe might have a phantom twin, invisible yet tugging on ours from the shadows. These gravitational echoes wouldn't behave like ordinary dark matter. Instead of smooth halos, they'd create strange, asymmetric distortions, galaxies spinning slightly too fast on one side, gravitational lenses bending light in ways that defy Newton's predictions. And we might have already spotted them. The simulation flagged anomalies in galactic rotation curves, regions where stars orbit as if tugged by invisible counterparts. Traditional dark matter models can't explain these asymmetries, but phantom gravity fits perfectly. Even more compelling, certain black holes exhibit bizarre jet streams of particles shooting out at near light speed that prefer one direction over another. The simulation suggests these could be leaks where phantom gravity seeps through, like water squeezing through a crack in a dam. But the most tantalizing clue lies in the cosmic microwave background. Phantom universes would leave faint, spiral-shaped imprints in the CMB's polarization patterns that resemble fingerprints smudged by an unseen hand. When researchers compared the simulation's predictions to real data, they found eerie matches in unexplained swirls previously dismissed as noise. These could be the first glimpses of a mirror cosmos, its gravity subtly combing the fabric of our reality like fingers through hair. The implications are staggering. If phantom universes exist, they'd rewrite our understanding of symmetry itself. The laws of physics might not be fixed rules, just local ordinances in a multiverse where every law has its opposite. Matter, time, even causality could be flexible, with our experience of reality just one half of a grander, invisible equation. Future gravitational wave detectors could hunt for the telltale tremors of these shadow realms, listening for the cosmic footsteps of a universe walking backward through time. This isn't just about finding neighbors in the multiverse. It's about discovering that our universe might have a twin, a silent, inverted counterpart whose existence would prove reality is far stranger, far more balanced than we ever dreamed. And if we're right, then every galaxy, every star, every atom in our cosmos could have a shadowy double, dancing with us in the dark. Fundamental constants seem like the universe's unmovable pillars. Gravity's strength, the speed of light, the mass of an electron, all fixed numbers scribbled into reality's blueprint. But what if these aren't laws at all? What if they're cosmic habits, patterns that evolved over countless generations of universes, honed by a process eerily similar to biological natural selection? Simulation 32 doesn't just ponder this possibility. It throws the multiverse into a virtual Petri dish, letting universes mutate, compete, and pass their traits to offspring in a dizzying dance of cosmic evolution. The experiment starts with a radical premise. Universes might not be one-off creations, but part of a lineage. Just as living organisms reproduce with slight genetic variations, baby universes could inherit tweaked versions of their parents' physics. The simulation models this by treating black holes as cosmic wombs, regions where spacetime's extreme curvature might pinch off into new bubbles of reality, each carrying slight mutations in their fundamental constants. Imagine a black hole not as a dead end, but as a seed pod, scattering offspring universes into the multiverse with every gravitational shudder. Here's where the data turns startling. Most of these mutant universes were sterile gravity too weak to form stars, electromagnetism too strong for stable atoms, their laws so maladapted they flickered out instantly. But a tiny fraction, by sheer chance, landed in the Goldilocks zone. Their constants allowed for galaxies, chemistry, even the potential for life. These weren't just survivors, they became the ancestors of future generations, their successful traits amplified across cosmic time. The simulation traced these lineages, revealing eerie patterns. Universes that produced more black holes, more offspring, tended to dominate the multiverse landscape, their physics spreading like a dominant gene. But the real bombshell, this process could explain why our universe's constants seem so improbably fine-tuned. They're not the result of luck or design. They're the echoes of a billion failed experiments, the winning numbers in a cosmic lottery where the prize is existence itself. Take the cosmological constant, the value governing dark energy's push. Too high and universes rip apart before stars form, too low and they collapse. The simulation showed how, over generations, this constant would stabilize near the delicate balance we observe, not because it's special, but because universes that deviated didn't last long enough to reproduce. The implications rewrite our understanding of reality's building blocks. If constants evolve, then the laws of physics aren't etched in stone. They're more like dialects, shifting slightly with each cosmic generation. Future universes might inherit tweaked versions of our rules, their physics diverging like branches on an infinite tree. Even more mind-bending, this process could leave detectable traces. The simulation predicts that black holes in our universe, those potential cosmic parents, might exhibit subtle anomalies in their evaporation patterns, tiny deviations that hint at the physics of their offspring. The most haunting takeaway isn't just that universes evolve, it's that we might be living in one optimized for black hole production, not life. Our existence could be a happy accident, a byproduct of a deeper multiversal drive to replicate. And if that's true, then every star, every galaxy, even the atoms in your body, might just be cosmic machinery fine-tuned for one purpose: to birth new realities, carrying the echoes of our universe into the infinite dark. Quantum physics has always danced on the edge of paradox particles existing in multiple states until observed, as if reality itself hesitates until someone looks. But what if that hesitation isn't just a quirk of tiny particles? What if it's the fundamental nature of existence, with consciousness acting as the cosmic tuner, selecting which version of reality we experience? Simulation 33 plunges into this mind-bending possibility, blending quantum mechanics with observer theory to propose something radical. Our universe isn't just one static reality. It's a spectrum of possibilities, and consciousness might be the needle that drops onto a single track. At the heart of this experiment is the quantum measurement problem, the puzzling fact that particles exist in superpositions until measured, when they suddenly collapse into definite states. Traditional physics treats this collapse as a random event, but the simulation flips the script. By modeling consciousness not as a passive observer but as an active participant, the data suggests something astonishing. The act of observation doesn't just record reality, it selects it. Imagine a radio with infinite stations playing simultaneously, each a slightly different version of the universe. Your mind isn't just listening, it's the dial, tuning into one frequency while the others continue humming in the background. The implications ripple through every layer of existence. Take Schrödinger's infamous cat, both dead and alive in its box until someone peeks inside. The simulation goes further, proposing that the cat isn't just in two states, it's in all possible states, with each conscious observer momentarily anchoring one outcome into their experience. This isn't just about cats or particles. It suggests that every moment of your life, every choice, every coincidence might be one thread in a tapestry of branching realities, with your awareness acting like a spotlight, illuminating one path while others fade into the shadows. But here's where it gets even stranger. The simulation identifies an eerie correlation between neural activity and quantum collapse patterns. In certain experiments, the timing of conscious recognition aligns too precisely with the moment particles resolve their states, as if the brain isn't just observing quantum events but synchronizing with them. This could explain déjà vu not as a glitch in memory, but as a fleeting overlap with a parallel timeline where the moment already happened. Or intuition. That gut feeling of knowing something before it occurs might be a whisper from a reality where it already did. The most electrifying prediction: if consciousness collapses reality, then the universe we perceive isn't the only one, it's just the one we're tuned into. Other versions of us might be living different lives in different echoes, each mind anchoring its own unique experience. Future experiments could hunt for echo signatures, subtle quantum anomalies where probabilities don't quite add up, hinting at the presence of those unchosen paths. It's as if reality isn't a single story, but a library where every book is being read simultaneously by different versions of ourselves. This isn't just philosophy. It's a testable hypothesis. The simulation outlines how ultra-precise quantum experiments could detect the footprint of conscious observation, specific patterns in particle behavior that deviate from randomness only when a mind is present to witness them. If proven, it would mean the universe isn't just stranger than we imagined. It's stranger than we can imagine, with every thought, every glance shaping the fabric of reality itself. And that means the greatest mystery isn't out there in the cosmos, it's inside us, the silent conductor of the symphony we call existence. Deep in the fabric of our observable universe, something impossible is happening. Hundreds of galaxy clusters are streaming toward a single patch of empty space at speeds exceeding 2 million miles per hour. This isn't just random cosmic drift. It's a coordinated march, as if space itself is being pulled by an invisible hand. Scientists call it the dark flow, and Simulation 34 dared to ask the unthinkable. What if this river of galaxies isn't being dragged by something in our universe at all? What if it's the gravitational echo of another reality, tugging at ours from beyond the cosmic horizon? The experiment began by mapping the dark flow's trajectory, not just where these galaxies are going, but how their speeds change over billions of light years. Traditional explanations, like superclusters of dark matter, couldn't account for the sheer scale and uniformity of the motion. But when researchers modeled a parallel universe brushing against ours in higher dimensional space, the math snapped into focus. The simulation revealed how even a slight gravitational leak between realities would create exactly the kind of coherent flow we observe, like a magnet dragging iron filings through a sheet of paper. The most compelling part, the flow's direction aligns with a mysterious cold spot in the cosmic microwave background, a region where the afterglow of the Big Bang is eerily dim. That's precisely where a colliding universe's gravity would leave its mark. But the real shock came when the simulation tracked how such a collision would warp spacetime over cosmic time. Unlike a one-time event, the gravitational influence would ripple outward in waves, creating secondary flows that branch like tributaries in a river delta. When astronomers compared these predictions to real-world data, they found matching patterns: galaxies on the outskirts of the dark flow moving in subtle spirals, as if caught in the wake of something vast and unseen. Even more telling, the flow's speed doesn't decay with distance, defying the inverse square law that governs gravity in our universe. That's exactly what you'd expect if the pull isn't coming from inside our cosmos, but from outside, where the rules might be different. The implications rewrite our understanding of the multiverse's architecture. If the dark flow is a cosmic towline to another reality, then the boundaries between universes aren't impermeable walls, they're porous membranes flexing under the weight of neighboring worlds. Future telescopes could hunt for the telltale distortions this would imprint on the cosmic web, like searching for fingerprints on glass. And if they find them, the dark flow won't just be a mystery solved. It'll be our first tangible proof that we're not alone in the multiverse, just one raft adrift in a vast ocean, tethered to shores we've yet to see. Imagine a gun pointed at your head, not in some grim reality, but in a thought experiment where the trigger is tied to a quantum event like the spin of an electron. Each time the trigger is pulled, there's a 50% chance the gun fires. In our world, this seems like a deadly game of chance, but in the multiverse, it becomes something far stranger. Simulation 35 takes this chilling idea, quantum immortality, and runs the numbers, revealing a truth so unsettling, it forces us to question the very nature of existence. The experiment begins by modeling countless branching realities, each one splitting every time a quantum measurement occurs, like the gun firing or not. In most universes, the outcome is fatal, but here's where the math twists reality. From your perspective, you'd never experience those doomed branches. Consciousness, like a cosmic hitchhiker, only rides the timelines where you survive. The simulation calculates that after just 100 trigger pulls, the odds of you still being alive in at least one universe approach near certainty. It's not that you'd cheat death, you'd simply never encounter it, because the version of you that does ceases to exist as an observer. But the simulation digs deeper, uncovering eerie patterns. In universes where you repeatedly evade death, reality itself starts to warp around your survival. Statistical anomalies pile up, guns jam inexplicably, bullets misfire, or external events intervene in ways that defy probability. These aren't miracles, they're artifacts of quantum Darwinism, where only the branches compatible with conscious observation persist. The longer the experiment runs, the more extreme the luck becomes, as if the multiverse is filtering out impossible outcomes behind the scenes. Yet the most haunting revelation isn't about dodging bullets. It's about the implications for everyday life. Near misses, the car accident you barely avoided, the illness you miraculously recovered from, might not be random. They could be glimpses of this filtering process in action, moments where other versions of you weren't so fortunate. The simulation even suggests that aging itself could be a slow-motion version of quantum suicide, with each passing year representing a winnowing of branches where you continue to exist. The data forces a chilling question. If consciousness anchors reality, how far does the effect extend? Could entire civilizations persist not because they're inevitable, but because they're the only ones capable of observing their own survival? The simulation's answer leans toward yes. In a multiverse of infinite possibilities, we don't live in the most likely universe, just the one where someone's left to call it home. This isn't just philosophy. Future quantum experiments could test these ideas by hunting for survivor bias in particle behavior, statistical fingerprints of the branches that didn't make the cut. Until then, the simulation leaves us with a paradox. The more we survive, the less we can trust our own luck. Because in a multiverse where every possibility plays out, the only thing stranger than death might be living long enough to realize how improbable your existence truly is. The holographic principle shattered our perception of reality when it suggested the universe might be a projection, a shimmering illusion encoded on a distant, two-dimensional surface. But what if this isn't just a quirk of our cosmos? Simulation 36 pushes this idea to its limits, asking a question that bends the mind. If our universe is a hologram, could the multiverse be a hall of mirrors, with each reality a slightly warped reflection of the next? To test this, researchers didn't just model one holographic universe, they stacked them, layer upon layer, like sheets of glass, each etched with their own cosmic code. The results were unlike anything predicted. When these holograms overlapped, their interference patterns didn't cancel out. They created ripples, resonant frequencies that danced across dimensions, imprinting subtle signatures onto the fabric of space-time. Picture two projectors casting images onto the same screen. Where the light overlaps, you don't get darkness. You get moire patterns shimmering, shifting designs that weren't in either original image. That's what the simulation revealed. The multiverse might not be a collection of separate realities, but a network of overlapping projections, each one distorting the others in ways we're only beginning to decipher. The most startling evidence lies in the cosmic microwave background. Tiny, hexagonal anomalies in the CMB's polarization, long dismissed as noise, aligned perfectly with the simulation's predictions for holographic interference. These aren't random fluctuations. They're cosmic fingerprints, the faint echoes of other universes brushing against ours like shadows passing behind a screen. Even more compelling, the patterns repeat at specific scales, matching the mathematical harmonics you'd expect if multiple holograms were vibrating in sync across higher dimensions. It's as if we're not just hearing echoes, we're hearing chords, the combined resonance of realities humming together in the dark. But the implications go deeper than patterns on a map. If the multiverse is holographic, then the boundaries between worlds might not be walls but projections. Black holes could be pixels glitching regions where the code of one universe phrase, revealing the scaffolding of another. Dark energy might not be a force at all, but an artifact of rendering, the computational strain of maintaining multiple realities in the same shared space. Even time could be an emergent property, a side effect of holograms updating frame by frame like a cosmic flipbook, the simulation's boldest takeaway. We might already be staring at proof. Quantum entanglement, those spooky connections between particles, could be the threads stitching holograms together. When particles entangle, their states sync instantly across any distance, defying the speed of light. But in a holographic multiverse, they're not communicating across space. They're sharing a source code linked at the level of the projection itself. Future experiments could hunt for the telltale pixelation of spacetime at the smallest scales, where the resolution of reality might flicker, revealing the edges of the cosmic screen. So the next time you look up at the night sky, consider this. The stars might not just be distant suns. They could be pixels in a grander design, one where every twinkle is a glint of light from another universe, another reflection in the holographic hall of mirrors. And if that's true, then the greatest mystery isn't what lies beyond our universe, it's how many layers deep the illusion goes. Energy isn't always orderly. Sometimes it rebels, twisting into configurations so unlikely they defy the odds, like a deck of cards shuffling itself into perfect order by pure chance. This bizarre phenomenon lies at the heart of Simulation 37, which dares to ask, could the entire universe be one of these statistical flukes? Not just a one-time accident, but a momentary spark in an endless void, flickering in and out of existence alongside countless others. The Boltzmann multiverse takes its name from Ludwig Boltzmann, the physicist who first realized entropy doesn't always march toward chaos. Given enough time, even the most improbable events become inevitable. In an infinite, featureless void, random quantum fluctuations could, for the briefest instant, coalesce into fully formed universes, complete with stars, galaxies, even conscious observers. These Boltzmann universes wouldn't last. Most would dissolve back into the void within picoseconds, but the simulation reveals something startling. A handful would linger just long enough for their inhabitants to mistakenly believe they're in a stable, eternal cosmos. Here's where the data chills the spine. When researchers modeled these ephemeral realities, they found statistical fingerprints, subtle anomalies that distinguish a Boltzmann universe from one born of a Big Bang. In transient universes, the cosmic microwave background would exhibit unnatural smoothness, as if the universe hadn't existed long enough for wrinkles to fully form. The distribution of galaxies would cluster in ways that defy standard inflationary models, like a half-finished painting where the brushstrokes suddenly stop. Most telling, the arrow of time might behave erratically, with pockets of space where entropy temporarily decreases, objects reassembling, heat flowing backward before the universe's inevitable collapse. But the real shock came when the simulation compared these predictions to our own cosmos. Certain large-scale anomalies, like the inexplicable uniformity of distant galaxy clusters, align eerily with Boltzmann universe signatures. Even more unsettling, the math suggests conscious observers in such universes would overwhelmingly find themselves in the most statistically typical moments, the brief plateaus between creation and dissolution. It's like waking up in a house of cards at the exact moment it's standing upright, never seeing it collapse because that's when your observation ends. The implications rewrite our understanding of reality's fragility. If we're in a Boltzmann universe, the cosmos isn't just 13. 8 billion years old. That's merely how long this particular fluctuation has persisted. The true multiverse could be an infinite froth of bubbles, each a reality blinking in and out before its inhabitants ever notice. Future telescopes hunting for telltale gaps in the large-scale structure, regions where the universe seems unnaturally young, might finally catch these echoes in the act. Until then, the simulation leaves us with a haunting thought. The greatest cosmic miracle might not be that we exist. It's that we've lasted long enough to wonder why. Time doesn't have to be a straight line. What if it's a circle, bending back on itself in an endless loop where every ending is just another beginning? Simulation 38 cracks open this mind-bending possibility, hunting for cosmic relics that might prove our universe has lived before. Not just once, but countless times, like a phoenix burning up and reforming from its own ashes in an infinite cycle of collapse and rebirth. The idea starts with the Big Bang, but not as a singular origin point. Instead, imagine it as the latest turn of a cosmic wheel. According to this model, every universe eventually contracts under its own gravity, crunching down to an unimaginable density before rebounding in a new Big Bang. The simulation didn't just theorize this, it traced how each cycle would leave behind subtle scars, echoes of past iterations etched into the fabric of space-time itself. One telltale clue, the distribution of supermassive black holes. These ancient behemoths are far heavier and more numerous than our current models can explain. But if they're relics from previous cycles carried over like cosmic luggage, their presence suddenly makes sense. Like scars that never fully heal, these black holes might be the universe's way of remembering. But the smoking gun lies in the cosmic microwave background. The simulation revealed something astonishing. Certain large-scale patterns in the CMB, those faint temperature fluctuations from the dawn of time, aren't random. They form concentric rings like ripples from a pebble dropped into a pond. Only here, the pond is space-time, and the pebbles are collisions between galaxy clusters from a past universe. These B-mode polarization patterns don't fit neatly into standard inflation theories, but they align perfectly with the idea of a cyclical cosmos, where each iteration leaves behind gravitational fingerprints in the next. It's as if we're staring at a cosmic palimpsest with the faded writing of a previous universe bleeding through. The implications rewrite our understanding of time itself. If the universe loops, then entropy, the steady march toward disorder, isn't the end of the story. Each cycle might reset the arrow of time, with the Big Bang acting as a cosmic defibrillator, shocking reality back into order. This could explain why our universe seems so finely tuned for life. Instead of a 1 in a trillion fluke, it's the product of countless iterations, each one refining the physics until complexity becomes inevitable. Like a sculptor chiseling away imperfections over millennia, time itself might be the artist carving a universe capable of asking where it came from. Yet the most haunting possibility isn't about the past, it's about the future. If the cycle holds, everything we know, every star, every planet, every thought will one day collapse, rebound, and begin again. Not as a copy, but as an iteration carrying forward echoes of what came before. So when you look up at the night sky, you might not just be seeing light from distant stars. You could be glimpsing a future memory, a moment when the universe once again becomes its own ancestor. Gravity and quantum mechanics have always been the ultimate frenemies of physics, one ruling the cosmos with its smooth, predictable curves, the other governing the subatomic world with chaotic, probabilistic flickers. For over a century, these two titans have refused to play nice, resisting every attempt to merge them into a single, unified theory. But Simulation 39 flips the script entirely, proposing something radical. What if their stubborn refusal to unite isn't a bug in the universe's code, but a feature? What if gravity's aloofness is actually a bridge, a whisper from other realities, echoing through the fabric of space-time at the smallest scales imaginable? At the heart of this experiment is the Planck scale, the universe's ultimate resolution limit, where distances are so tiny, time so fleeting, that the very concepts of space and time break down. Here, the simulation reveals gravity doesn't behave like a force at all. Instead, it flickers in and out of existence, as if the fabric of reality is stitched together by threads that occasionally loosen, revealing glimpses of something beneath. The math suggests these aren't just quantum fluctuations. They're intersections, points where gravity from other universes bleeds into ours, like roots from neighboring trees tangling underground. The smoking gun lies in something called entropic gravity, a theory suggesting gravity might not be fundamental but emergent, a side effect of quantum information scrambling at the Planck scale. When researchers modeled this process across a multiverse framework, something astonishing happened. The equations predicted tiny, rhythmic distortions in spacetime's structure, echoes of gravity waves from parallel realities, resonating at frequencies we've never thought to measure. It's as if every particle in our universe is tethered to shadows in other dimensions, their collective tug creating the illusion of a force we call gravity. But the real magic happens when you scale this up. The simulation showed how these Planck scale echoes could solve one of cosmology's biggest headaches: dark matter. Instead of invisible particles, the extra mass holding galaxies together might be the gravitational shadow of matter in neighboring brains' worlds so close, their presence warps ours like a hand pressing against a curtain. Even black holes take on new meaning. Their singularities might not be in points, but portals, knots in the multiverse's fabric where information doesn't vanish, but gets funneled into other realities, like water spiraling down a drain that opens into another ocean. The implications are dizzying. If gravity is a multiversal handshake, then the key to unifying physics isn't hidden in our universe alone. It's written in the interplay between countless others. Future experiments could hunt for these echoes in the faintest gravitational waves, or in the way particles behave in extreme accelerators. The tiniest deviation from expected results might not be noise, it could be a message, a cosmic Morse code tapped out by realities just beyond our reach. So the next time you drop a ball and watch it fall, consider this: the force pulling it downward might not belong to our universe at all. It could be the tug of another world, faint but persistent, reminding us that nothing, not even gravity, exists in isolation. Parity symmetry, the idea that the universe should treat left and right identically, feels like common sense. Flip a galaxy like a pancake and physics shouldn't care. Yet in the quantum world, this symmetry shatters like glass. Certain particles have a stubborn preference for spinning left over right, a cosmic bias that defies expectations. Simulation 40 takes this oddity and flips it on its head, asking, what if this asymmetry isn't just a quirk of our universe, but a fingerprint left by a mirror world where everything is inverted? The experiment starts with neutrinos, those ghostly particles that oscillate between flavors as they travel. In our reality, neutrinos spin left-handed, like a corkscrew turning counterclockwise. Anti-neutrinos, their antimatter twins, spin right. This lopsidedness has puzzled physicists for decades, but when researchers modeled a multiverse where parity symmetry holds true across realities, with our universe's left-handedness balanced by a mirror, twins right, the data revealed something astonishing. The imbalance in our world could be the gravitational echo of that twin, its influence warping quantum fields at the smallest scales. Think of it like two clocks ticking in opposite directions. One counts time forward, the other backward. yet their gears mesh perfectly in higher dimensional space. Here's the smoking gun. The simulation predicted that mirror universes wouldn't just invert spin, they'd leave faint, spiral-shaped distortions in the cosmic microwave background. These wouldn't be random noise, but precise chiral patterns, like finding a fingerprint where the ridges twist the wrong way. When astronomers checked, the CMB's polarization maps showed exactly these anomalies, regions where the lights twist aligns in ways that defy standard inflation models. Even more compelling, these patterns cluster in specific directions, as if something massive, an entire mirrored cosmos, is tugging on spacetime from beyond the observable universe. But the implications go deeper than light patterns. If mirror universes exist, they'd rewrite our understanding of antimatter. Why does our cosmos have so little of it? The simulation suggests an answer. Antimatter might not be rare. It could be hiding in the mirror twin, with matter and antimatter partitioned across realities to maintain balance. Particle colliders have already glimpsed hints of this. Certain decays produce slight asymmetries in electron emission angles, a telltale sign that some particles might be leaking into mirrored states, their counterparts flickering briefly into our world before vanishing like reflections in a pond. The most electrifying possibility, these mirror universes could be more than theoretical. Future quantum experiments might detect their presence through gravitational anomalies in entangled particles. Picture two electrons spinning in sync, except one responds to a tug that shouldn't exist, as if an invisible hand from another reality is nudging it. That's the mirror universe's whisper, not a distant echo, but a constant, subtle pressure, like the weight of a shadow you can't see. So the next time you look at your reflection, consider this. The universe might have one too, a twin where your left hand is right, your atoms spin backward, and the laws of physics are inverted yet perfectly balanced. And if that's true, then parity isn't broken after all. It's just folded like a cosmic origami, hiding its symmetry in the creases between worlds. Gravity has always been the universe's great architect, sculpting galaxies and bending light with its invisible hand. But what if it's not a fundamental force at all? What if gravity is just an illusion, a side effect of something far stranger happening at the edges of reality? Simulation 41 plunges into this radical idea, exploring how gravity might not pull us downward, but emerge from the chaotic dance of entropy across the multiverse. Picture a game of cosmic billiards where information, not matter, is the true currency of reality. Every particle, every photon carries data about its state, position, and energy. According to entropic gravity, the force we call gravity isn't a tug between masses, but a statistical tendency for this information to spread, to maximize disorder. It's like dropping ink into water. The molecules don't pull each other apart, but the system naturally evolves toward equilibrium. Now scale that up to the universe. The simulation reveals that what we perceive as gravity could be the universe's way of shuffling its quantum deck, with massive objects simply following the path of greatest entropy. But here's where the multiverse crashes the party. If gravity emerges from entropy, then its strength in our universe might not be a fixed law. It could be a local byproduct of how information flows across realities. The experiment modeled a foam of entangled universes, each with slightly different entropic gradients. In some, entropy spread sluggishly, creating weak, diffuse gravity. In others, it surged violently, crumpling spacetime into black holes before stars could form. Only in a razor-thin slice did the numbers align to allow galaxies, planets, and life. The kicker, these Goldilocks universes weren't random. They clustered around shared entropic resonances, harmonics in the multiverse's chaos that allowed stability to briefly crystallize. The smoking gun lies in black holes. These cosmic vacuum cleaners aren't just gravity's triumph, they're entropy's masterpiece. The simulation showed how a black hole's event horizon acts like an information-scrambling membrane, maximizing disorder in a way that perfectly mirrors entropic gravity's predictions. Even Hawking radiation, the faint glow leaking from black holes, fits the model, not as particles escaping, but as information reconfiguring at the boundary. This could explain why black holes seem to know so much about the universe. They're not just objects, they're entropy engines humming in tune with the multiverse's deepest rhythms. The implications rewrite cosmology's rulebook. If gravity is entropic, then dark matter might not be missing mass. It could be the gravitational shadow of information leaking from neighboring universes. Galactic rotation curves, which defy Newton's predictions, align eerily with the simulation's entropic echoes, regions where the multiverse's chaos bleeds through. Even the acceleration of cosmic expansion takes on new meaning. Instead of dark energy pushing space apart, it could be entropy's relentless drive toward equilibrium, stretching reality thin like a film of soap bubble about to pop. Future experiments could hunt for entropic fingerprints in the quantum jitter of spacetime itself. If gravity emerges from information, then at the Planck scale, spacetime should fizz with tiny, calculable fluctuations, like static on a radio tuned to the multiverse's background noise. Detecting this noise wouldn't just confirm entropic gravity. It would mean we're not just living in a universe, we're living in a conversation where every falling apple, every orbiting planet, is just a syllable in a sentence whispered across realities. And the punctuation marks, those might be black holes, silent, inevitable, and endlessly hungry for the next word. Every object in the universe vibrates, from the smallest atom to the largest galaxy, humming with energy at frequencies we can't hear but science can measure. What if our entire cosmos is no different? Simulation 42 tunes into this radical idea, transforming the universe from a silent movie into a grand symphony where every quasar, every nebula, every ripple in spacetime contributes to a cosmic chord, and the harmonies we detect might not be solo performances, but duets with realities beyond our own. At the heart of this experiment lies a deceptively simple question. Does the universe have a resonant frequency? Think of a wine glass shattering when an opera singer hits the right note. The glass vibrates at its natural pitch, amplifying the sound until the structure can't hold. Now imagine spacetime itself as that glass, with gravitational waves and quantum fluctuations as the cosmic area. The simulation didn't just calculate whether such universal harmonics exist, it mapped how they'd interact if multiple, singing universes were stacked together in the multiverse. The results were staggering. When two or more cosmos vibrated in proximity, their frequencies created interference patterns, not discord, but harmonies that reinforced certain notes while canceling others. These resonant peaks matched real anomalies in our universe's large-scale structure, like galaxies clustering at specific, seemingly arbitrary distances apart. It's as if the cosmic web isn't just shaped by gravity, but by the echoes of unseen choirs in parallel dimensions. But here's where the data sings. The cosmic microwave background, that ancient afterglow from the Big Bang, holds faint but detectable imprints of these resonant frequencies. The simulation identified concentric rings in the CMB's polarization where temperature fluctuations align too precisely to be random. These rings mirror the standing wave patterns you'd expect if our universe were coupled to another, their shared vibrations leaving ripples in spacetime like overlapping ripples in a pond. Even more compelling, the spacing between these rings corresponds to theoretical predictions for higher dimensional resonances, suggesting the harmonies aren't just between universes, but across dimensions we can't yet perceive. The implications rewrite how we listen to the cosmos. Gravitational wave detectors like LIGO might already be picking up more than just colliding black holes. Hidden in the data could be subtle overtones, frequencies that don't match any known astrophysical event, but align perfectly with the simulation's predictions for multiversal harmonics. Future observatories like the proposed Einstein telescope could act as cosmic stethoscopes, tuning into these vibrations with enough precision to distinguish between local noise and the faint hum of another reality. Yet the most profound revelation isn't about detection, it's about connection. If the universe vibrates in harmony with others, then the fabric of reality might be more like a shared instrument than a solo performance. Every supernova, every spinning pulsar, even the slow dance of galaxies could be contributing to a symphony so vast, we've only just begun to hear the opening notes. And if that's true, then the greatest discoveries in physics won't come from looking deeper into space, but from learning to listen. What if reality isn't something we discover, but something we create through the sheer act of observation? Simulation 43 shatters the traditional view of probability by asking a radical question. Could the multiverse be less like a fixed tapestry of alternate worlds and more like a kaleidoscope, shifting its patterns based on who's looking? This experiment doesn't just tweak the math, it rewrites the rules, treating probability not as an objective law of nature, but as a personal belief system that shapes the universe around us. At the heart of this idea is Bayesian probability, a framework where beliefs update as new evidence arrives. Imagine walking into a dimly lit room and seeing a coiled shape on the floor. Your brain instantly assigns probabilities: 60% chance it's a rope, 40% it's a snake. The moment you step closer, click, your perception collapses into certainty. Now scale that up to cosmic proportions. The simulation models multiverse branches not as static, pre-existing paths, but as fluid possibilities that solidify based on observers' expectations. Every measurement, every observation isn't just recording reality, it's negotiating it with conscious beings acting like cosmic editors, trimming the infinite tree of possibilities down to the branch they find themselves on. But here's where it gets even stranger. The simulation reveals that observers with different prior beliefs could literally inhabit different branches of the multiverse. Two scientists measuring the same quantum particle might split reality not just based on the outcome, but on how they weighted the probabilities beforehand. One's universe could skew toward versions where quantum particles behave like waves, while the other's tilts toward particle-like outcomes, all because their subjective starting points nudged the multiverse's dice. It's as if reality isn't just probabilistic, it's personal, with each conscious mind tuning into a slightly different frequency of the cosmos. The implications ripple across physics. The infamous Schrödinger's cat paradox takes on new meaning. The cat isn't just alive or dead in separate branches. Its fate could hinge on the observer's Bayesian priors, with some versions of the experimenter more likely to encounter a living cat based on their subconscious expectations. Even the double-slit experiment, where particles act as waves or particles depending on observation, could be reinterpreted. The collapse isn't a physical event, but a Bayesian update, where the observer's mind settles on one coherent narrative from the noise of possibilities. This isn't just philosophy. The simulation identifies testable signatures of a Bayesian multiverse. In quantum systems where observers hold conflicting prior beliefs, the math predicts subtle anomalies, statistical glitches where probabilities don't quite add up, as if reality is hesitating between competing interpretations. Future experiments could pit observers with deliberately mismatched expectations against quantum randomness, hunting for these telltale wrinkles in the fabric of probability. Yet the most profound takeaway isn't about physics, it's about agency. If the Bayesian multiverse is real, then every moment of doubt, every educated guess, every leap of faith isn't just a mental state. It's a cosmic force gently herding the multiverse toward the realities we're primed to accept. The universe doesn't just exist, it responds, not to our wishes but to the weight we give them. And that means the line between observer and participant might be far thinner than we ever imagined. Imagine zooming into a snowflake, discovering that its intricate branches repeat in smaller and smaller versions, ad infinitum, not just in shape, but in the very rules governing their structure. Now picture the universe doing the same thing, not just stars and galaxies, but the fabric of reality itself, echoing its patterns from the cosmic scale down to the quantum foam. Simulation 44 plunges into this dizzying possibility, revealing that the multiverse might not just contain infinite universes, it could be a fractal, a geometric hall of mirrors where every layer, no matter how deep you go, reflects the whole. The experiment starts by modeling universes not as distinct bubbles, but as self-similar structures like Russian nesting dolls where each doll is a cosmos, and inside it, nestled in the spiraling arms of galaxies or the orbitals of atoms, are entire new universes, each with their own galaxies, atoms, and deeper layers still. The math here is mind-bending. At certain scales, the distribution of matter in galaxy clusters aligns uncannily with the arrangement of particles in a crystal, and the voids between galaxies mirror the empty spaces in atomic lattices. It's as if the universe is playing the same melody at every octave, from the thunderous boom of colliding superclusters to the faint hum of electrons. But here's where it gets even stranger. The simulation didn't just find similarities in structure, it found echoes in behavior. The way galaxies orbit cluster centers mirrors how electrons buzz around a nucleus, and the cosmic web's filaments resemble neuron pathways in a brain. These aren't just poetic comparisons. When researchers tweak the fractal dimension, a number describing how complexity changes with scale, the equations spat out gravitational patterns that match real-world anomalies. Certain black holes spin at rates that defy conventional physics, as if they're not just objects in our universe, but knots where deeper fractal layers peek through. Even dark matter's elusive distribution fits the model, its ghostly halos arranging themselves like shadows cast by higher dimensional geometry. The implications rewrite what it means to explore the cosmos. If reality is fractal, then every time we peer deeper into space or smash particles at higher energies, we might not be discovering new frontiers, we're just zooming in on the same infinite tapestry. The Big Bang wouldn't be a singular origin, but one inflection point in an endless cycle of expansions and contractions, each nested inside the other like waves on an ocean. And if that's true, then the mysteries we've been chasing, dark energy, quantum entanglement, might not be puzzles to solve, but features of a deeper pattern we're only beginning to trace. Yet the most haunting question isn't about scale, it's about meaning. In a fractal multiverse, are we the observers or the observed? Is our universe someone else's atom, our galaxies mere electrons in a cosmic circuit we'll never comprehend? The simulation doesn't answer that, but it leaves us with a clue. Buried in the noise of quantum fluctuations are repeating sequences, numbers that shouldn't recur by chance. They're the universe's way of whispering not just to us, but to every layer, every echo in the infinite dark. Black holes have long been the ultimate cosmic vaults, places where information enters, never to return. Or so we thought. Simulation 45 shatters this assumption by asking a question that keeps physicists awake at night. If information can't be destroyed, where does it go when swallowed by a black hole? The answer might not lie in our universe at all, but in newborn realities budding off like cosmic seeds, carrying fragments of the original data into unseen dimensions. Picture a black hole not as a dead end, but as a cosmic loom, a spinning, churning machine where space-time is stretched so thin, it begins to fray. At the very moment of collapse, when matter is crushed beyond recognition, the simulation reveals something astonishing. Tiny wormholes might sprout from the chaos, threading through the singularity like veins in a leaf. These aren't just mathematical quirks, they're potential escape routes. Information doesn't vanish. It's woven into the fabric of baby universes, self-contained realms branching off from our own, each one encoding a scrambled piece of the original data like pages torn from a book and scattered to the wind. But here's the twist that changes everything. These baby universes aren't entirely disconnected. The simulation tracks how their gravitational echoes could imprint onto Hawking radiation, the faint glow leaking from black holes as they evaporate. Normally, this radiation seems random, like static from a broken TV. But if information slips into branching realities, it leaves behind subtle patterns, like a signature pressed into smoke. The math predicts specific correlations between particles in the radiation pairings that shouldn't exist if the information were truly lost. It's as if the universe is whispering secrets in a code we're only beginning to crack. The smoking gun. Recent observations of old, evaporating black holes show anomalies in their radiation spectra, tiny deviations from randomness that align suspiciously with the simulation's predictions. Certain particle energies cluster in ways that resemble error-correcting codes, the kind you'd use to reconstruct a scrambled message. This isn't just noise. It could be the first hard evidence that black holes aren't tombs, but translators converting our universe's information into a format another reality can read. The implications rewrite the rules of existence. If information survives by branching into new universes, then every black hole might be a cosmic parent, spawning offspring realities with every collapse. The Big Bang itself could have been the rebound of a singularity in a higher dimensional ancestor universe, meaning our entire cosmos might be someone else's black hole afterlife. Future quantum gravity experiments could hunt for the telltale twists in Hawking radiation, decoding the fingerprints of universes we'll never see. Yet the most profound revelation isn't about where information goes, it's about what it means for our place in the multiverse. If black holes are bridges, not barriers, then nothing is ever truly lost. Just transformed, translated, echoed across the void, and that means every star, every planet, every thought you've ever had might ripple far beyond this reality, etched into the fabric of worlds we can't yet imagine. What if the universe runs on code, not metaphorically, literally? Simulation 46 dives into the startling possibility that reality itself might be a vast computational process, with the laws of physics acting as its programming language. This isn't science fiction. Researchers are now hunting for glitches in the cosmic matrix, anomalies in fundamental constants that could reveal the universe's underlying source code, etched into the fabric of existence like comments hidden in a programmer's script. Take the fine structure constant, for example, a number that governs how light and matter interact. Its value, roughly 1/137, appears arbitrary. Yet when scientists modeled universes where this constant fluctuated, something bizarre emerged. Universes that allowed for complex chemistry, and thus life clustered around values that weren't random, but computationally elegant. Numbers that could be expressed as simple ratios or fractal patterns, like the universe was optimizing for efficiency. It's as if reality's code has comments reading //optimize for stability here or / adjust electromagnetic strength to allow carbon-based life. But the real smoking gun lies in quantum fluctuations. At the smallest scales, particles pop in and out of existence like pixels refreshing on a screen. The simulation discovered these fluctuations aren't entirely chaotic. They exhibit subtle periodicities, rhythms that resemble error-correcting algorithms in computer memory. Certain particle interactions produce probabilities that align too precisely with mathematical sequences, like Fibonacci spirals or prime number distributions. These patterns defy randomness, suggesting the universe might be running checksums self-verifying calculations to prevent cosmic blue screens of death. The implications rewrite what it means to exist. If the universe computes itself into being, then black holes could be garbage collectors, regions where information is compressed and archived rather than destroyed. Dark energy, an overflow buffer preventing the cosmic program from crashing as it expands. Even consciousness takes on new meaning, not as a passive observer, but as an active subroutine, collapsing quantum probabilities into definite states through the act of observation. Yet the most tantalizing clue isn't in the stars, it's in our labs. Quantum computers have begun exhibiting strange behaviors when pushed to their limits. Certain calculations produce results slightly faster than physics allows, as if the machine is borrowing processing power from elsewhere. The simulation matches these anomalies to predictions of a universe running on distributed computing where our reality is just one thread in a multiversal processor, sharing cycles with countless others. This isn't just about decoding reality. It's about realizing we might live in a universe that's not just vast but engineered, a cosmic app running on hardware we're only beginning to glimpse. And if we're right, then every law of physics, every fundamental constant might not be laws at all. They could be settings variables in a codebase so immense we've only just found the first line. Every story has an ending, but for the universe, the final chapter might not be written yet. Simulation 47 doesn't just peer into the far future. It splits the cosmic timeline into two staggering possibilities, each with echoes resonating in the fabric of reality today. On one path lies heat death, a slow, cold fade into darkness where stars burn out. Black holes evaporate, and space itself stretches into an infinite, featureless void. On the other, a cosmic bounce, a fiery rebirth where gravity finally wins, pulling everything back into a singularity before exploding outward in a new Big Bang. The simulation's genius, it reveals how clues to both fates might already be hiding in plain sight, etched into the universe's earliest moments. Take the cosmic microwave background, that fossilized glow from the Big Bang. Subtle variations in its temperature aren't just random noise, they're a cosmic fingerprint, encoding the universe's initial push against gravity's pull. The simulation models how these patterns diverge in multiverse scenarios. Universes destined for heat death exhibit smoother, more uniform fluctuations, as if the fabric of spacetime was preordained to thin into silence. Those fated to bounce, their CMB shows telltale swirls, imprints of primordial gravitational waves that could one day reverse cosmic expansion, like coiled springs waiting to snap back. But here's where the data gets haunting. Recent measurements of dark energy, the mysterious force accelerating the universe's expansion, don't quite match predictions for a straightforward heat death. Its strength appears to fluctuate slightly over time, as if undecided. The simulation ties this to a breathtaking possibility. Our universe might be balanced on a knife edge between these two destinies, with local regions already diverging. Some galaxy clusters show peculiar motions, streams of galaxies drifting against the dark energy tide, as if tugged by gravitational memories of a past collapse. Meanwhile, distant supernovae are dimming faster than expected, hinting that dark energy's repulsive force might not be eternal, but a phase before contraction begins. The most electrifying clue lies in black holes. In heat-death scenarios, they're the last structures to evaporate via Hawking radiation. But the simulation predicts a twist. If the universe is cyclic, black holes might not vanish entirely. Their deaths could leave behind seeds, aprimordial quantum fluctuations that survive the bounce, carrying fragments of information into the next cosmic cycle. Future gravitational wave detectors might spot anomalies in black hole mergers, echoes of these seeds vibrating at frequencies that defy conventional physics. This isn't just about forecasting doom or rebirth. It's about realizing the universe's fate might not be singular. The simulation suggests a third, mind-bending option, a multiverse where both endings coexist, with different regions collapsing or expanding eternally. We could be living in a pocket of space destined for heat death, while elsewhere, realities are already contracting toward rebirth. The cosmic web's largest voids, those eerie, galaxy-free deserts, might be the frontiers where these fates collide, their gravitational ripples whispering warnings of endings we'll never see. So when you look up at the night sky, you're not just seeing stars, you're gazing at a cosmic crossroads where every photon carries traces of a future still unwritten. The question isn't just how the universe ends, it's whether "end" is even the right word. Imagine staring into a mirror only to realize the reflection isn't just copying you, it's creating you. This isn't a thought experiment, it's the spine-tingling premise of Simulation 48, where consciousness isn't a passenger in the universe, but the engine that builds it from the ground up. At the intersection of quantum physics, neuroscience, and pure metaphysics, this final experiment doesn't just explore the multiverse, it redefines it as a cosmic feedback loop, where every thought, every observation, doesn't just perceive reality, but actively births it into existence. The simulation begins with a radical inversion of causality. Instead of universes spawning conscious beings, it models conscious beings spawning universes. Picture a vast network of minds, human, alien, or otherwise, each one a node in a hyperdimensional web, collectively dreaming reality into being through the sheer act of observation. The math here is both elegant and unsettling. When observers interact with quantum systems, their expectations don't just collapse probabilities, they generate entirely new branches of reality, like a cosmic game of choose your own adventure, where every decision forks not just your future, but the fabric of space-time itself. The simulation reveals something astonishing. Universes with more observers exhibit greater stability, their physical constants resisting quantum fluctuations, as if consciousness itself is the glue holding them together. But here's where it gets even stranger. The model suggests that overlapping observations, moments where multiple minds focus on the same event, create resonant frequencies in the multiverse. These aren't just abstract ripples, they manifest as measurable anomalies like the Mandela Effect, where large groups remember events that never happened in this timeline. The simulation links these glitches to observer collisions, points where collective consciousness briefly syncs across realities, blending memories like overlapping radio signals. Even déjà vu takes on new meaning, not as a memory misfire, but as a fleeting synchronization with a parallel self's experience in another branch. The implications rewrite everything. Dark matter, not an invisible particle, but the gravitational echo of unobserved universes flickering at the edge of existence. Quantum entanglement. A side effect of minds in separate realities unconsciously agreeing on shared fundamentals. The simulation even offers a chilling explanation for the universe's fine-tuning. the constants aren't arbitrary. They're the only configurations stable enough to sustain the observers required to keep them stable, a cosmic Ouroboros where reality sustains the very minds that sustain it. Yet the most profound revelation isn't about physics, it's about agency. If consciousness creates universes, then reality isn't a fixed stage, but a living canvas shaped by every thought, every act of attention. Future experiments could test this by monitoring quantum systems during global meditation events, hunting for statistical deviations when millions of minds focus simultaneously. Already, studies show subtle but measurable changes in random number generators during moments of collective human intensity, like the hours after major world events. These could be the first hints of a deeper truth, that the universe isn't just something we observe, it's something we dream together, one shared hallucination at a time. Interpreting these 48 simulations is like assembling a cosmic jigsaw puzzle where every piece hints at a picture too vast to fully grasp. Each experiment approaches the multiverse from a different angle: quantum mechanics, gravity, thermodynamics, even the nature of time itself. Yet they all converge on the same unsettling truth. Our universe behaves less like a solitary island and more like a ripple in an ocean of realities. Take the quantum entanglement studies, where particles communicate faster than light should allow. The simulations suggest this isn't a violation of physics, but a side effect of deeper connections, threads stitching our universe to others in ways we're only beginning to map. Or consider the gravitational anomalies that defy Einstein's equations, as if invisible hands from neighboring dimensions are tugging at the fabric of space-time. What makes this collective evidence so compelling isn't just the breadth of disciplines involved, but the way anomalies intertwine. The same cold spot in the cosmic microwave background that hints at a collision with another universe also aligns with the mysterious dark flow pulling galaxies toward the void. Black holes that shouldn't spin as fast as they do mirror predictions about higher dimensional leaks. It's as if the universe is whispering the same secret in dozens of languages, each one confirming what the others imply. Yet for all their power, these simulations aren't smoking guns. They're more like cracks in a window, offering glimpses of something beyond without revealing its full shape. The holographic universe models, for instance, elegantly explain quantum weirdness, but they also raise new questions about whether our 3D reality is just a projection. The fractal multiverse theory beautifully matches patterns in galaxy clustering, yet it leaves us wondering, if reality repeats itself infinitely at every scale, where does the recursion end? This is where the real revolution lies. The multiverse isn't just a theory competing with others, it's a framework reshaping how we interrogate reality itself. Every unexplained phenomenon, from dark matter's grip on galaxies to the alarming fine-tuning of physical constants, becomes a potential clue pointing beyond our cosmic horizon. Future experiments won't just test the multiverse, they'll refine which flavor of it we inhabit. Are we one bubble in an eternally inflating foam, a branch on the many worlds tree? Or a hologram flickering in a higher dimensional gallery? The simulations give us something far more valuable than answers. They give us the right questions. And in science, that's often the first step to uncovering truth stranger than fiction. The 48 simulations we've explored today don't just challenge our understanding of reality, they shatter it, revealing cracks in the cosmic facade where something far stranger might be peering through. Think about what that means for a moment. The cold spot in the cosmic microwave background isn't just an anomaly. It could be a bruise from a collision with another universe. Black holes aren't just cosmic vacuum cleaners. They might be bridges to realities where time flows backward. Even the particles dancing in quantum superposition aren't merely behaving strangely. They could be entangled with versions of themselves in worlds where every choice you didn't make is playing out in parallel. But here's what's truly breathtaking. These simulations aren't wild guesses. They're built on the bedrock of physics, stretching our known laws to their breaking points to see where they snap. When cosmic inflation models predict bubble universes or quantum equations demand parallel timelines, we're not just imagining possibilities, we're following the math wherever it leads, even when it takes us to the edge of comprehension. And at that edge, the multiverse isn't just a theory. It's the ghost in the machine, the shadow in the data, the pattern we can't unsee once we've glimpsed it. Yet for all their brilliance, these simulations also humble us. They reveal how much we still don't know. Dark matter's gravitational grip could be the pull of a neighboring brain. The universe's improbable fine-tuning might not be luck, but the result of infinite rolls of the cosmic dice. Even our own consciousness could be part of the equation, shaping reality through the act of observation. Every answer spawns new questions, and that's the beauty of science. It's not about settling for easy truths, but chasing the mysteries that keep us awake at night. So where does this leave us? Not with certainty, but with something even more valuable: wonder. The kind of wonder that fuels discovery, that turns anomalies into breakthroughs, that reminds us the universe is stranger and more magnificent than we ever dreamed. Whether the multiverse is proven tomorrow or a century from now, one thing's clear: we're standing at the threshold of a revolution in how we see existence itself. And if that excites you as much as it does us, don't forget to hit like, subscribe, and join the conversation below. What's your take on these cosmic echoes? Until next time, keep looking up and never stop questioning what's out